Hello there and welcome to Cosmos for Sleep. Tonight, we're embarking on a serene journey to explore the colossal gas giant Jupiter. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. Jupiter holds the title as the largest planet in our solar system, a truly immense gas giant. Its sheer mass is so profound that it outweighs all the other planets in our solar system combined. To grasp its scale, imagine that more than 1,300 Earths could comfortably fit inside Jupiter's colossal volume. One of Jupiter's most iconic features, a truly immense and captivating sight, is the Great Red Spot. This persistent, swirling storm, a majestic atmospheric vortex, stretches across vast expanses of Jupiter's cloud tops and is wider than our entire planet Earth. Its colossal size allows it to comfortably contain multiple Earth-sized worlds within its gentle, rotating embrace. This remarkable and enduring storm has been observed for at least 350 years, a quiet testament to its enduring power and the long-term stability of Jupiter's atmospheric processes. Its continuous existence over centuries paints a vivid picture of a consistent, powerful system, constantly in motion, yet maintaining its grand elliptical form with a serene, almost ancient presence. This subtle yet profound feature showcases the immense scale of atmospheric phenomena possible on gas giants, far beyond what we experience on our terrestrial home. The Great Red Spot is a calm, enduring spectacle, a testament to the planet's internal energies and the vastness of its atmospheric dynamics, a silently swirling crimson eye observing the distant cosmos. Jupiter harbours a fascinating and profound secret within its immense structure. It nearly became a star. This colossal gas giant, a grand assembly composed primarily of hydrogen and helium, shares the fundamental elemental building blocks of our Sun. Intriguingly, it would have required only about 80 times its current majestic mass to ignite the delicate and powerful process of nuclear fusion within its core. Had it gathered more material during the solar system's early, formative years, our stellar neighbourhood might have hosted two suns, subtly transforming its celestial landscape and profoundly influencing the evolution of all orbiting bodies. This potential for stellar birth speaks volumes to Jupiter's profound scale and its fundamental composition, closely mirroring that of a nascent star, a quiet echo of a cosmic path not taken. This near-stellar status highlights Jupiter's unique place as a celestial body that almost transcended its planetary designation, forever carrying the legacy of its near ignition. Furthermore, Jupiter possesses the most powerful magnetic field of any planet in our solar system. This unseen, yet immensely influential force field is tens of thousands of times stronger than Earth's own protective magnetic shield, extending gracefully far into the surrounding space, enveloping its moons and a vast region beyond. This immense and pervasive magnetic field creates stunning auroras at Jupiter's poles. Painting cosmic light shows far grander and more expansive than any seen on our homeworld. These ethereal displays of light, born from the intricate interaction of charged particles with Jupiter's powerful magnetic lines, shimmer with a serene elegance, illuminating the planet's polar regions with vibrant, delicate hues of blues and reds. The sheer scale of these auroras, dwarfing Earth's own, underscores the profound energetic processes at play within Jupiter's magnetosphere, a constant silent dance of cosmic forces that continually reshape the environment around the giant planet. Jupiter spins with remarkable speed, completing a full rotation in just 9 hours and 55 minutes, making it the fastest rotating planet in our solar system. This rapid, unhurried rotation imparts a subtle, yet noticeable effect on the planet's overall shape. It gently flattens Jupiter at its poles and causes a graceful bulge at its equator, transforming its perfect spherical form into a slightly oblate spheroid. This dynamic and continuous motion contributes significantly to the planet's complex weather patterns and the striking horizontally banded appearance of its atmosphere, creating a constant, majestic flow. The rapid spin also influences the powerful internal dynamo that generates its immense magnetic field, linking its rotation to its profound unseen forces and shaping the distribution of its atmospheric layers. This swift, patient rotation is a fundamental aspect of Jupiter's majestic character. Beyond its own grand and solitary presence, Jupiter boasts an impressive collection of celestial companions, with 95 confirmed moons, a greater number than any other planet in our solar system. This vast and diverse entourage of natural satellites creates a miniature, intricate solar system, each moon quietly orbiting the colossal gas giant, contributing to a complex gravitational ballet. 4 of these moons, its largest and most famous, are known collectively as the Galilean moons. They were first observed by the keen and revolutionary eye of Galileo Galilei in the year 1610, a pivotal discovery that subtly challenged the prevailing geocentric model of the universe and forever changed our understanding of our place within the cosmos. These 4 worlds, each unique, represent a diverse collection of celestial bodies, offering endless opportunities for serene scientific contemplation. Among these Galilean moons, Europa is believed to harbour a vast subsurface ocean of liquid water, serenely nestled beneath its icy crust. Scientists estimate this hidden ocean holds more liquid water than all of Earth's oceans combined, making it a place of profound scientific interest and a tantalizing prospect for future exploration. This immense, tranquil body of water, gently warmed by persistent tidal forces exerted by Jupiter's powerful gravity, represents one of the most promising locations in our solar system to search for the subtle signs of life beyond Earth, hinting at possibilities beneath its frozen veil. The smooth, cracked surface of Europa offers delicate clues to the hidden world below, a silent invitation to uncover its aquatic secrets. Io, another of Jupiter's Galilean moons, presents a strikingly different and incredibly dynamic character. It is the most volcanically active body in our entire solar system, adorned with hundreds of active volcanoes that continuously and gently reshape its surface. This constant geological activity, fueled by the immense tidal forces exerted by Jupiter's gravity as Io orbits, creates a dynamic, ever-changing landscape where plumes of sulfurous material gently rise high above the surface before settling back down, constantly refreshing its colourful, mottled appearance. The sheer scale of this volcanism is a testament to the powerful gravitational embrace of its parent planet, transforming Io into a vibrant, ever-renewing world, a cosmic forge of new landscapes. Ganymede stands as the largest moon in the solar system, a colossal satellite that surpasses even the planet Mercury in its grand size. Its vast, icy surface and complex geological history make it a world of quiet wonders, hinting at past tectonic movements and cryovolcanic flows. Intriguingly, Ganymede is also the sole moon in our solar system known to possess its own magnetic field. This unique and subtle feature, likely generated by a convective liquid iron core deep within its interior, adds another layer of complexity to this already remarkable celestial body, making it a truly unique member of Jupiter's family. Its dual nature, both a moon and a magnetic world, offers a serene puzzle for cosmic exploration. Finally, Callisto, the 4th Galilean moon, presents a very ancient, heavily cratered surface, a quiet canvas marked by eons of cosmic impacts. This placid and unchanging appearance hints at a tranquil geological history, with little evidence of the internal activity that continuously reshapes its sister moons. Its surface serves as a cosmic archive, meticulously preserving the subtle imprints of impacts from billions of years ago, offering a serene glimpse into the early, formative years of our solar system. Each of these moons, distinct in its nature and geological story, contributes to the rich tapestry of Jupiter's cosmic realm. Quietly orbiting the colossal planet, each is a world of its own, waiting patiently for our calm, curious gaze to uncover its enduring secrets. The subtle interplay of gravity, light, and matter creates a symphony of celestial movements, a gentle ballet unfolding across unimaginable distances. As we drift through this cosmic neighbourhood, we appreciate the quiet grandeur of Jupiter and its family, a serene reminder of the universe's endless wonders. Our journey continues, carried by the soft currents of cosmic knowledge, as new facts gently unfold. Jupiter plays a truly crucial role as a cosmic guardian within our solar system, a silent, powerful protector. Using its immense gravitational pull, this colossal planet gently deflects or absorbs many comets and asteroids that might otherwise drift perilously towards the inner solar system. This constant, subtle interception of celestial wanderers has, over billions of years, undoubtedly spared Earth and its neighbouring planets from countless impacts, acting as a benevolent shield against the potential chaos of space. Its steadfast presence in the outer solar system is a testament to its profound influence, quietly sweeping the cosmic pathways clear for the smaller inner worlds. This protective function is a majestic, unhurried dance of gravity, preserving the delicate balance of our planetary neighbourhood. The giant planet also possesses a unique characteristic. It emits more heat than it receives from the distant sun, a subtle and intriguing indication of a significant internal heat source that resides deep within its vast interior. This surplus of radiant energy, quietly escaping into space, suggests an ongoing dynamic process beneath its swirling cloud tops. This internal warmth is largely generated by the slow, patient gravitational contraction of the planet's immense mass over eons, a gradual settling process that releases colossal amounts of energy. As the planet's vast hydrogen and helium mass subtly compresses under its own colossal weight, potential energy is transformed into thermal energy, providing a steady, gentle warmth that continually radiates outwards, a soft glow from within. Moreover, Jupiter possesses a faint ring system, a delicate and understated celestial adornment. This subtle feature was a surprising discovery made by the Voyager 1 spacecraft in the year 1979, revealing a previously unseen aspect of the gas giant. Unlike the prominent icy rings of Saturn, which are bright and easily observed, Jupiter's rings are primarily composed of tiny, dark dust particles. These minuscule grains are gently kicked up from the surfaces of its small inner moons by micrometeoroid impacts, forming a diffuse and ethereal structure that gracefully encircles the planet, a quiet, almost invisible halo. This delicate ring system is a testament to the subtle interactions between Jupiter's moons and the cosmic dust that perpetually drifts through its expansive gravitational domain. Jupiter's atmosphere is predominantly composed of hydrogen and helium, mirroring the fundamental elemental composition of our Sun. This makes the giant planet a vast gaseous sphere of the universe's most abundant elements, a cosmic mirror reflecting the primordial material from which stars are born. Beneath its swirling outer atmosphere, where the pressure becomes almost unimaginable, scientists believe Jupiter harbours a vast ethereal ocean of liquid metallic hydrogen. This exotic state of matter, where hydrogen atoms are compressed so intensely that their electrons become detached and move freely, behaves more like a liquid metal than a gas. This unique substance acts as an excellent electrical conductor, quietly generating Jupiter's powerful and expansive magnetic field through a colossal internal dynamo. Deep within Jupiter's atmosphere, under these same unimaginable pressures and intense temperatures, scientists theorize that carbon might be compressed into diamonds, potentially leading to a serene and sparkling phenomenon known as diamond rain. This theoretical process suggests that carbon-rich compounds, subjected to extreme conditions, could crystallize into precious gemstones, gently falling through the planet's dense layers. This fascinating possibility paints a picture of a hidden, sparkling realm within the gas giant, a quiet transformation of matter under cosmic forces. Jupiter has been a familiar and captivating sight to ancient civilizations across the globe for millennia. Easily visible due to its remarkable brightness and distinct appearance in the night sky, it has long held a special place in human observation and mythology. The planet's name itself is derived from the king of the Roman gods, reflecting its majestic and dominant presence in the celestial sphere, a powerful and revered entity. This ancient naming convention underscores the profound impression Jupiter made on early stargazers, recognizing its grand scale and influential position among the visible planets. Over the decades, several robotic missions have journeyed to Jupiter, each a testament to human curiosity and technological ingenuity. These intrepid explorers include Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, and Juno, each meticulously gathering data and offering new insights into its nature. The Juno mission, currently in orbit around Jupiter, is diligently studying its composition, its gravitational field, its powerful magnetic field, and the captivating auroras in its polar regions. This ongoing mission provides an unprecedented close-up view of the giant planet, continually unveiling its secrets with calm, scientific precision. Jupiter's immense gravitational influence also helps to sculpt the asteroid belt, a region of rocky debris located between Mars and Jupiter. Its powerful presence gently prevents a full-sized planet from fully forming in that region, instead maintaining a dynamic collection of smaller bodies. This subtle gravitational shaping ensures the asteroid belt remains a dispersed collection of remnants, rather than coalescing into a single, larger world, a quiet testament to Jupiter's role in organizing the solar system's architecture. The planet emits powerful bursts of radio waves, quiet signals that are detectable from Earth with specialized receiving equipment. These radio emissions are generated by the intricate interactions between Jupiter's immense magnetic field and the charged particles trapped within its magnetosphere. These subtle cosmic whispers, traveling across vast distances, offer another window into the energetic processes occurring around the giant planet, allowing scientists to listen to its dynamic environment. The Galilean moons, locked in their elegant orbits, experience intense tidal heating, a gentle warming caused by Jupiter's powerful gravitational pull. This constant rhythmic stretching and squeezing of the moon's interiors generates friction, which in turn produces heat. This internal warmth powers their diverse geological activities, from the volcanism of Io to the potential subsurface oceans of Europa and Ganymede, creating active and evolving worlds under Jupiter's gentle yet firm gravitational embrace. Finally, Jupiter's distinctive banded appearance, a breathtaking sight of alternating light-coloured zones and darker belts, arises from the complex dynamics of its vast atmosphere. These zones and belts are created by atmospheric currents flowing in opposite yet harmonious directions, forming a majestic global circulation pattern. The lighter zones are regions of upwelling gas, while the darker belts are regions where gas is gently sinking, creating a continuous, serene dance of atmospheric movement. This intricate interplay of gases and currents paints Jupiter's surface with its iconic stripes, a calm and beautiful display of cosmic weather patterns. The subtle hues observed in Jupiter's clouds, ranging from creamy whites to deep reds and browns, are thought to arise from complex chemical reactions involving trace elements like sulfur and phosphorus. These elements, present in small quantities within the vast hydrogen and helium atmosphere, react under the influence of sunlight and internal heat, gently adding to the visual majesty and ever-changing artistry of the giant planet's appearance. This chemical ballet creates the beautiful, swirling colours that captivate our gaze. Beneath these colourful, swirling cloud tops, scientists theorize about Jupiter's enigmatic core. If it indeed exists as a solid structure, it is believed to be rocky and possess a mass about 10 to 15 times that of Earth. This dense central region, hidden deep within the planet's immense gaseous envelope, represents the foundational building block around which the colossal gas giant slowly accumulated its vast atmospheric layers. This hypothetical core, under unimaginable pressures, would be a silent, super-dense heart to the majestic planet, anchoring its colossal structure. The upper atmosphere of Jupiter experiences remarkably fast winds, reaching astonishing speeds of up to 340 miles per hour. These powerful, yet constant atmospheric flows contribute significantly to the dynamic weather system that defines Jupiter's appearance, creating the distinct banded patterns and persistent storms. These swift currents are a testament to the immense energy at play within the planet's atmosphere, a continuous, unhurried motion that shapes its visible face. Jupiter's orbital journey around the Sun requires nearly 12 Earth years to complete. This lengthy and measured cosmic dance around our star illustrates the vast distances involved and the stately pace of celestial mechanics in the outer solar system. This extended orbital period means that each Jovian year encompasses multiple Earth years, highlighting the different scales of time within our planetary neighbourhood, a patient, unhurried revolution. Despite its immense size, Jupiter's average density is surprisingly low, less than 1.5 times that of water. This characteristic underscores its nature as a gas giant, composed primarily of light elements like hydrogen and helium, rather than dense rock. If a body of water large enough could exist, Jupiter would gracefully float upon it, a gentle behemoth of gas and liquid, its low density a defining feature of its colossal form. In addition to the famous Great Red Spot, Jupiter's atmosphere is home to many smaller storms, each contributing to its turbulent beauty and dynamic weather. These numerous vortices, though less famous than their colossal counterpart, also swirl and interact, adding to the intricate, ever-changing patterns visible from afar. Some of these smaller atmospheric storms can persist for years or even decades, evolving slowly and subtly within the gas giant's vast expanse, a testament to the enduring nature of Jupiter's atmospheric dynamics. Jupiter's powerful magnetosphere, an immense protective bubble of magnetic force, extends millions of miles into space far beyond the planet itself. This vast magnetic shield acts as a colossal, unseen barrier, interacting with the solar wind and charged particles from the Sun. This magnetosphere effectively traps these charged particles, forming intense radiation belts that encircle Jupiter. These belts, regions of high-energy radiation, are so strong they present a significant challenge and a delicate balance for any visiting spacecraft, requiring robust shielding to protect sensitive instruments from their powerful, pervasive influence. Jupiter's gravity significantly influences the orbits of comets throughout the solar system. Its immense gravitational pull acts as a cosmic shepherd, sometimes gently guiding them inward towards the Sun, potentially leading to spectacular impacts, or outward into the quiet depths of deep space, subtly altering their long elliptical paths. This constant gravitational interaction helps to maintain the delicate order of the outer solar system, a continuous, unhurried shaping of cosmic trajectories. The planet's obliquity, or axial tilt, is very small, measuring just over 3 degrees. This minimal tilt means Jupiter experiences no significant seasonal changes, unlike Earth with its distinct seasons. Its atmospheric patterns and temperatures remain largely consistent throughout its long orbital year, creating a more uniform, yet still dynamic climate across its vast surface. This lack of tilt contributes to the stable, banded appearance of its atmosphere, a serene consistency in its cosmic posture. Jupiter's atmosphere lacks a clearly defined solid surface. Instead, as one descends into its interior, the gaseous hydrogen and helium gradually transition from gas to liquid, and then to the exotic state of metallic hydrogen, without any sharp boundary. This seamless, gradual transition means there is no solid ground to land upon, only an ever denser, ever hotter fluid, a profound journey through states of matter. The internal pressure deep within Jupiter is millions of times greater than Earth's atmospheric pressure, a testament to its colossal scale and the immense weight of its overlying atmospheric layers, creating an environment of unimaginable force. Jupiter's moon, Europa, is considered extraterrestrial life, primarily due to its hidden subsurface ocean. This vast body of liquid water, shielded by an icy crust, offers a potentially stable environment where life could quietly flourish, fueled by tidal heating and chemical reactions. The tantalizing prospect of life beneath Europa's frozen shell makes it a prime target for future gentle robotic exploration, inspiring profound scientific curiosity. The Great Red Spot, though remarkably long-lived, is gradually shrinking over time. While its exact future remains an intriguing cosmic mystery, its diminishing size is a subtle reminder that even the most enduring features of gas giants are subject to slow, patient change. Its remarkable longevity, however, continues to fascinate scientists, a quiet testament to the resilience and dynamic nature of Jupiter's atmospheric systems. Jupiter's delicate ring system is continually replenished by dust particles gently ejected from its 4 small inner moons, Metis, Adrastea, Amalthea, and Thebe. These tiny moons, constantly bombarded by micrometeoroids, shed minute amounts of dust that then disperse to form the faint, ephemeral rings, a continuous subtle cycle of creation and dispersal. This gentle replenishment ensures the rings maintain their ethereal presence, a quiet interaction between moons and dust. Finally, the temperature in Jupiter's upper atmosphere can descend to a chilling negative 234 degrees Fahrenheit. This extreme coldness in the outer layers contrasts sharply with the immense heat generated deep within its core, illustrating the vast range of thermal conditions across the giant planet's immense structure. This frigid upper atmosphere creates a serene, yet inhospitable environment, a constant reminder of the extreme conditions found in the outer reaches of our solar system. Each of these subtle characteristics contributes to the grand, complex portrait of Jupiter, a world of quiet power and enduring mystery. Our journey through its wonders continues, unfolding with gentle cosmic grace. Deep within Jupiter's immense interior, where pressures are extreme and matter takes on exotic forms, the temperatures are thought to reach astonishing levels, exceeding 43,000 degrees Fahrenheit. This immense heat, a testament to its internal energy and ongoing gravitational contraction, makes Jupiter a world of profound internal warmth, a subtle glow at its heart that radiates outwards through its vast layers of hydrogen and helium. This internal furnace plays a crucial role in driving the planet's atmospheric dynamics and generating its powerful magnetic field, a silent, powerful engine at the core of the gas giant. The planet's immense gravitational pull significantly influences the stability and delicate balance of the entire solar system. Acting as a celestial anchor, Jupiter's colossal mass subtly guides the orbits of other planets, asteroids, and comets, ensuring a harmonious and predictable cosmic dance. Without its stabilizing presence, the inner solar system might have experienced a far more chaotic and disruptive history, a testament to Jupiter's quiet yet profound influence on its celestial neighborhood. Jupiter's cloud tops are a mesmerizing canvas for swirling vortices and powerful lightning storms. These atmospheric electrical discharges are much larger and more energetic than any found on Earth, illuminating the vast cloud layers with brilliant, fleeting flashes. The lightning observed on Jupiter is believed to be associated with water clouds in its atmosphere, drawing a subtle parallel to Earth's weather phenomena, even amidst the vastly different conditions of a gas giant. This connection suggests similar fundamental processes generating electrical storms, despite the colossal scale of Jupiter's atmospheric systems. Jupiter's largest moon, Ganymede, is believed to harbour a vast saltwater ocean, gently nestled beneath its thick, icy crust. This hidden reservoir, potentially holding more water than Earth's oceans, represents another tantalizing possibility for the existence of liquid water beyond our home planet. The presence of salt would further enhance the potential for complex chemical interactions, inspiring hopes for future exploration into this intriguing subsurface world, a calm, hidden sea beneath the ice. Callisto, uniquely among the Galilean moons, shows very little evidence of tidal heating. This characteristic suggests a less active and more serene interior compared to its geologically dynamic siblings like Io and Europa. Its ancient, heavily cratered surface, largely untouched by significant internal forces, speaks to a placid and unchanging history. A quiet world that has preserved its primordial features over billions of years, a testament to its tranquil cosmic journey. The King of Planets has been a subject of human observation since at least the 7th or 8th century before Christ, captivating stargazers and inspiring myths for millennia. Its prominence made it easily identifiable, a guiding light for ancient cultures. Early telescopic observations by Galileo Galilei, beginning, revealed Jupiter's 4 largest moons, this groundbreaking discovery, which placed Earth at the centre and quietly opened humanity's eyes to a more heliocentric, sun-centred understanding of our cosmic home, a gentle revolution in scientific thought. The Pioneer 10 spacecraft achieved a significant milestone, becoming the first to gently fly past Jupiter in December of 1973. This pioneering mission provided humanity with its first close-up images and data of the giant planet, offering unprecedented insights into its complex nature. Following this, the Galileo probe made history as the first spacecraft to orbit Jupiter, meticulously studying the giant planet from 1995 to 2003. The Galileo mission provided a wealth of information, deepening our understanding of Jupiter's atmosphere, moons, and magnetosphere, a patient, sustained exploration. Jupiter's profound gravitational influence played a crucial role in clearing out much of the debris in the early solar system. Its colossal mass acted as a cosmic broom, gently sweeping up or ejecting countless asteroids and planetesimals, shaping the current architecture of our planetary neighborhood. This early gravitational sculpting prevented many smaller bodies from coalescing into additional planets, contributing to the distinct separation between the rocky inner planets and the gas giants of the outer solar system, a subtle yet powerful force of cosmic organization. the planet's powerful, its immense magnetic field, and the charged particles within its magnetosphere. These energetic processes create a chorus of radio waves, silent to the human ear but detectable by specialized instruments. These radio emissions are so strong that, with the right specialized equipment, they can be quietly detected here on Earth using amateur radio telescopes. This remarkable phenomenon allows enthusiasts to listen to the distant dynamic activity around Jupiter, a subtle cosmic symphony. Jupiter's rapid rotation creates a phenomenon known as differential rotation, where various parts of its atmosphere gently spin at different rates. This means that the equatorial regions rotate slightly faster than the polar regions, contributing to the shearing forces that help maintain the planet's distinct banded appearance. This complex yet harmonious atmospheric movement is a key factor in the enduring patterns and dynamics observed in Jupiter's cloud tops, a continuous, unhurried dance of gases. The lighter zones in Jupiter's atmosphere are generally regions of upwelling gas, where warmer, less dense material gently rises, bringing fresh compounds to higher altitudes. Conversely, a cooler, denser material descending into the planet's interior. This continuous cycle of rising and sinking gases creates the alternating bands of colour and texture that define Jupiter's majestic appearance, a subtle yet grand atmospheric conveyor belt. Jupiter's atmospheric composition includes subtle amounts of methane, ammonia, water vapour, and other complex compounds, in addition to its dominant hydrogen and helium. These trace elements contribute to the varied chemical reactions and the vibrant coloration seen in its cloud layers, adding intricate detail to its vast gaseous envelope. The metallic hydrogen layer is thought to extend for tens of thousands of kilometers deep within the planet's interior, a colossal ocean of exotic matter under immense pressure. This deep conductive layer is crucial for generating Jupiter's powerful magnetic field, a silent, unseen engine driving many of the planet's most profound characteristics. Our tranquil journey through the wonders of Jupiter continues, revealing more of its serene and majestic secrets with each passing moment. Jupiter's powerful magnetic field, a vast and unseen force, is tilted by approximately 10 degrees relative to its rotational axis. This subtle inclination, rather than being perfectly aligned, contributes to its complex magnetic environment and the intricate patterns observed in its auroras. This tilt adds a layer of dynamic interplay, creating a more intricate dance between the planet's rotation and its energetic magnetosphere, a quiet complexity in its cosmic shield. The presence of water ice on Europa's surface makes it a prime candidate for future astrobiological missions, inspiring hopes of discovery. This icy shell, with its potential for a hidden ocean beneath, holds the tantalizing prospect of liquid water and the possibility of life, making Europa one of the most compelling targets for gentle robotic exploration in our solar system. The allure of this frozen world, with its promise of hidden depths, continues to draw the gaze of scientists. Jupiter's atmosphere is thoughtfully divided into many distinct layers, each possessing different temperatures and pressures, creating a complex vertical structure. From the frigid upper reaches to the intensely hot and dense depths, these layers form a vast multi-tiered gaseous envelope. The deepest layers of Jupiter's atmosphere remain largely a mystery to scientists, offering an ongoing frontier for exploration, a profound realm yet to be fully unveiled by our calm, curious gaze. This unknown territory hints at even more exotic states of matter and dynamic processes waiting to be discovered. Jupiter's extensive system of 95 confirmed moons resembles a miniature solar system, each moon a diverse and fascinating world in its own right. From the volcanically active Io to the potentially life-harbouring Europa, and the massive Ganymede with its own magnetic field, this collection of celestial companions provides a wealth of scientific study. Each moon quietly orbits, a serene and intricate cosmic dance around their grand parent. However, the intense radiation surrounding Jupiter, trapped within its powerful magnetosphere, could gently break down organic molecules. This poses a significant challenge for the emergence of life near the planet itself, creating an environment that is largely inhospitable to known biological processes on the larger scale. While the hidden oceans of some moons might offer protection, the immediate vicinity of Jupiter is a realm of profound energetic forces. Jupiter's gravitational influence extends even to the distant Kuiper belt, a region of icy bodies far beyond its immediate vicinity. Its colossal mass subtly shapes the orbits of these distant objects, gently guiding their paths and influencing the overall distribution of material in the outer solar system. This far-reaching gravitational tug demonstrates Jupiter's pervasive role in the grand architecture of our cosmic neighborhood, a silent, powerful sculptor of distant realms. The planet's gravitational tugs cause small rhythmic oscillations in the Sun's movement, a subtle effect that exoplanet hunters utilize to detect other planets around distant stars. As Jupiter orbits, its gravity gently pulls on the Sun, causing it to wobble slightly. This technique, known as the radial velocity method, allows astronomers to infer the presence of unseen planets by observing these minute stellar movements, a clever application of cosmic mechanics. Jupiter's atmosphere has no clear, defined boundary between its gaseous and liquid states. It is instead a gradual, seamless transition. As one descends deeper into the planet, the gas becomes progressively denser and hotter, eventually reaching a point where it behaves more like a liquid without any distinct surface. This continuous transformation of matter is a profound characteristic of gas giants, where the distinction between atmosphere and interior blurs into a single vast fluid realm. The atmospheric pressure at the base of Jupiter's visible clouds is about 10 times that of Earth's sea level, highlighting the immense forces at play within its colossal gaseous envelope. This incredible pressure, a testament to the sheer weight of the overlying atmosphere, crushes gases into denser states, driving the exotic physics of Jupiter's interior. It is an environment of profound physical power, far beyond our terrestrial experience. Jupiter's moon, Amalthea, exhibits an unusual potato-like shape, a gentle consequence of its small size and close orbit around the giant planet. Its irregular form is a result of its relatively weak gravity not being strong enough to pull itself into a perfect sphere, allowing its original, uneven shape to persist. This charmingly irregular moon is a quiet reminder of the diverse forms that celestial bodies can take, a subtle deviation from planetary perfection. Some of Jupiter's smallest moons are believed to be captured asteroids, gently pulled into its gravitational embrace over cosmic time. These minor celestial bodies, wandering through the solar system, found themselves within Jupiter's powerful sphere of influence and were subsequently drawn into stable orbits. This process of gravitational capture adds to the diverse collection of moons orbiting the gas giant, each with its own unique origin story. The planet's powerful gravity can gently pull in and ultimately absorb comets, as was dramatically observed with Comet Shoemaker-Levy 9 in 1994. This comet, fragmented by Jupiter's tidal forces, made a spectacular series of impacts into the planet's atmosphere. This cometary impact left dark, swirling scars on Jupiter's atmosphere that remained subtly visible for several months, a quiet testament to the giant planet's role as a cosmic absorber, a majestic event witnessed across vast distances. Jupiter's atmosphere contains helium in roughly the same proportion as the early universe, offering a glimpse into primordial conditions. This consistent ratio of hydrogen to helium, largely unchanged since the solar system's formation, provides valuable clues about the composition of the early cosmos and the processes that led to the creation of stars and planets. It is a quiet, chemical link to the universe's fiery beginning. The planet's immense size and mass make it the true gravitational anchor of the outer solar system, a silent, powerful presence that dictates the dynamics of its celestial neighborhood. Its dominant gravitational influence shapes the orbits of its numerous moons and the trajectories of countless other bodies, maintaining a stable and predictable cosmic order. Jupiter stands as a colossal, enduring force, a silent sentinel in the distant reaches of our Sun's domain. The Great Red Spot rotates in a counterclockwise direction, much like a high-pressure system here on Earth, a majestic atmospheric ballet. This consistent rotational direction, maintained for centuries, highlights the enduring stability of this colossal storm. Its slow, patient swirl is a testament to the powerful yet harmonious atmospheric forces that shape Jupiter's most iconic feature, a continuous, unhurried dance of gases across its vast, colourful surface. Our serene journey continues, gently unfolding more of Jupiter's profound and beautiful cosmic narrative. Jupiter's subtle ring system is composed of 4 main delicate components, each contributing to its ethereal beauty. These include the halo, the main ring, and 2 fainter gossamer rings. These gossamer rings are gracefully named after the moons Amalthea and Thebe, which gently supply their dust, a continuous subtle interaction that maintains their delicate structure. This intricate arrangement of rings, though not as visually prominent as Saturn's, speaks to the complex dynamics within Jupiter's immediate environment. Jupiter experiences strong wind shears between its atmospheric bands, creating intricate patterns of flow and interaction. These differences in wind speed and direction between the lighter zones and darker belts generate turbulence and contribute to the formation and longevity of its many storms, a continuous, unhurried atmospheric ballet. The Juno mission, currently in orbit, has revealed surprising new details about Jupiter's deep interior and the enigmatic nature of its powerful magnetic field. Its data provides unprecedented insights into the planet's hidden depths, deepening our understanding of its internal processes and the source of its immense magnetic forces, a patient unveiling of cosmic secrets. Jupiter's moon, Io, experiences extreme tidal forces, subtly stretching and squeezing it like a flexible sphere as it orbits the colossal gas giant. This powerful tidal heating, generated by the constant gravitational tug-of-war, is precisely what fuels Io's intense and continuous volcanism, making it the most geologically active body in our solar system. This constant internal friction keeps Io in a state of perpetual geological transformation, a vibrant, active world under Jupiter's powerful influence. The icy surface of Europa is crisscrossed with mysterious lines and cracks, delicate patterns that hint at ongoing subsurface activity. These intricate markings are believed to be evidence of the moon's dynamic icy shell interacting with the vast saltwater ocean hidden beneath, suggesting a world where internal forces are constantly yet subtly reshaping its exterior. These delicate features are a silent invitation to explore the hidden depths below, a promise of ongoing geological motion. Ganymede's expansive surface shows subtle evidence of tectonic activity in its distant past, suggesting a dynamic history that included periods of internal heating and movement of its icy crust. While not as active as Io, Ganymede's grooved terrain and distinct regions speak to a complex geological evolution over billions of years, a quiet reshaping of its colossal form. This past activity adds another layer of intrigue to the solar system's largest moon, a testament to its long unfolding story. Jupiter's magnetic field creates a vast magnetotail, a luminous extension stretching hundreds of millions of miles behind the planet flowing away from the Sun. This impressive magnetotail, a cosmic streamer of charged particles, can extend gracefully beyond the orbit of Saturn, showcasing the immense reach and profound influence of Jupiter's magnetic field across the outer solar system. It is a silent, energetic plume, constantly shaped by the solar wind, a testament to Jupiter's colossal magnetic power. Jupiter's atmosphere possesses a complex chemistry, hinting at the potential for the formation of organic molecules within its vast gaseous envelope. While conditions are extreme, the presence of various elements and energetic processes offers a tantalizing possibility for the building blocks of life to form, even in this unlikely environment. This complex chemical dance adds a layer of subtle potential to the gas giant's already fascinating composition. The planet's gravitational influence was undeniably crucial for the formation and subsequent gentle evolution. Cosmic maestro, Jupiter's immense mass sculpted the protoplanetary disk, cleared out debris, and subtly influenced the orbits of all other celestial bodies, guiding the early development of our planetary neighborhood. Its presence ensured the stable and predictable arrangement we observe today, a silent, powerful force shaping cosmic destiny. Jupiter continues to be a dynamic and evolving world, constantly revealing new secrets through patient scientific exploration. With each passing mission and every new observation, our understanding deepens, unveiling more of its intricate processes, from the depths of its core to the outermost reaches of its magnetosphere. It is a world of continuous discovery, a testament to the endless wonders of the cosmos. Jupiter's atmosphere hosts high-altitude hazes of ammonia ice, contributing to its layered cloud structure and its distinctive pale coloration. These delicate icy crystals, suspended high above the main cloud decks, play a role in reflecting sunlight and shaping the planet's overall visual appearance, adding to the serene beauty of its atmospheric canvas. The planet's polar regions feature unique cyclone clusters observed by the Juno spacecraft, arranged in stable geometric patterns. Unlike the more chaotic storms in other areas, these polar cyclones organize themselves into elegant, enduring formations, a surprising and beautiful display of atmospheric order. These polar cyclones are long-lived, calmly swirling for years, a testament to Jupiter's enduring atmospheric dynamics and the profound stability of these high-latitude phenomena. Jupiter's magnetosphere interacts with the solar wind, creating a vast bow shock where these cosmic flows meet. This invisible boundary, akin to a ship's wake in water, marks the point where the solar wind is gently deflected around Jupiter's magnetic shield, a continuous, subtle collision of cosmic forces. This interaction is a dynamic dance between the Sun's outgoing particles and Jupiter's powerful magnetic protection. Finally, the Munoz volcanoes constantly replenish Jupiter's magnetosphere with sulfur dioxide gas. The continuous eruptions on Io eject vast quantities of this gas into space, where it becomes ionized and trapped within Jupiter's magnetic field. This constant influx of material contributes to the magnetosphere's energetic environment, creating a dynamic interplay between the volcanic moon and its colossal parent, a subtle yet powerful exchange of cosmic matter and energy. A quiet unfolding of cosmic grandeur, a quiet unfolding of cosmic grandeur. Jupiter's powerful radiation fields, an invisible yet pervasive force, can gently strip electrons from atoms, creating an intense and energetic environment around the planet. These fields, born from the trapping of charged particles within its vast magnetosphere, form a silent, powerful aura that envelops Jupiter and its inner moons. This constant interaction underscores the dynamic nature of the gas giant, where even unseen forces profoundly shape its surroundings, a continuous, subtle dance of energy. The gas giant's immense gravity acts as a subtle, cosmic vacuum cleaner, patiently drawing in stray space debris that wanders into its powerful sphere of influence. This gentle, yet persistent, gravitational pull helps to clear the orbital paths in the outer solar system, preventing many potential impacts on its moons and other celestial bodies. It is a quiet cleansing of the cosmic neighborhood, a testament to Jupiter's colossal mass and its role in maintaining a delicate balance. Deep within Jupiter's interior, scientists believe that its rocky core may be surrounded by a layer of super-hot, super-dense fluid. This exotic state of matter, far removed from anything experienced on Earth, contributes to the planet's internal heat and dynamic processes. This mysterious, internal ocean of compressed elements represents another frontier of understanding, hinting at the profound transformations matter undergoes under extreme cosmic pressures, a silent, powerful heart to the colossal world. The planet's rapid rotation, completing a turn in just under 10 hours, creates powerful jet streams in its atmosphere. These swift, persistent currents gracefully carve out the familiar banded appearance that defines Jupiter's majestic visual identity. The continuous motion of these atmospheric rivers, flowing in alternating directions, sculpts the planet's visible face into a breathtaking display of cosmic weather, a perpetual, unhurried artistic creation. Jupiter's moon, Europa, has a remarkably smooth, icy surface with very few impact craters, suggesting a young and subtly geologically active exterior. This pristine appearance hints at ongoing processes that continually resurface the moon, erasing the marks of cosmic collisions over time. Indeed, this smooth surface hints at a process where fresh ice is gently brought up from below, possibly by cryovolcanism, where water or slush erupts onto the surface and freezes, subtly renewing its frozen landscape. The subsurface ocean on Europa, hidden beneath its icy shell, is thought to be warmed by persistent tidal forces, keeping the water in a liquid state. This delicate balance, maintained by Jupiter's powerful gravitational tugs, is crucial for the potential habitability of this intriguing moon. The continuous flexing and squeezing of Europa's interior generates enough friction to prevent its vast ocean from completely freezing, creating a serene, hidden realm of liquid water. Jupiter's moon Io, in stark contrast, experiences continuous resurfacing due to its constant volcanic activity, perpetually erasing older craters and features. This relentless geological dynamism, fueled by intense tidal heating, ensures that Io's surface is one of the youngest and most vibrant in the solar system, a world in a constant state of gentle transformation. The material ejected from Io's numerous volcanoes, primarily sulfur and sulfur dioxide, forms a gentle donut-shaped cloud of plasma called a torus around Jupiter. This ethereal ring of glowing particles is a visible manifestation of Io's profound activity, subtly contributing to Jupiter's energetic magnetosphere. Ganymede's expansive surface displays both ancient, heavily cratered terrain and younger, grooved regions, suggesting complex geological processes that have shaped its appearance over billions of years. The coexistence of these distinct landforms tells a story of varied epochs, from intense bombardment to periods of internal activity. The grooves on Ganymede, intricate linear patterns across its icy crust, are believed to be the result of past tectonic activity or ice flows, a subtle reshaping of its crust as internal forces gently moved its surface material. This quiet, ancient dynamism adds to the allure of the solar system's largest moon. Callisto's ancient surface, a stark contrast to its more active siblings, is one of the most heavily cratered in the solar system, indicating a placid and largely unchanging history. Its pristine record of impacts speaks to a lack of significant geological activity, preserving a cosmic archive of events from the early solar system. Callisto's interior is not fully differentiated, meaning its rock and ice may not have completely separated into distinct layers, suggesting a quieter and less energetic evolution compared to Europa, Io, and Ganymede. This lack of internal churning has allowed its surface to remain a serene testament to cosmic time. The intricate interaction between Jupiter's vast magnetosphere and its moon Io creates a powerful electrical current. This energetic connection, born from Io's movement through Jupiter's magnetic field, generates some of the planet's powerful radio emissions, transforming orbital motion into detectable signals. This electrical current, known as the Io flux tube, subtly links the moon to the giant planet, creating an invisible, yet powerful, energetic bridge between them, a continuous exchange of energy across vast distances. Jupiter's atmosphere contains traces of phosphine, a gas that scientists use to study the planet's deep atmospheric circulation. The presence and distribution of this compound provide valuable clues about the complex movements of gases far beneath the visible cloud tops, offering a window into the otherwise hidden dynamics of Jupiter's lower atmosphere. This subtle chemical tracer helps astronomers unravel the intricate, unhurried flows within the gas giant. Finally, the planet's immense gravity helps maintain the stability of the entire solar system, keeping other planets in their predictable, harmonious orbits. Jupiter's colossal mass acts as a gravitational anchor, subtly influencing the paths of all celestial bodies and preventing more chaotic interactions. This profound, silent influence ensures the long-term order and predictability of our cosmic home, a continuous, gentle guardianship over the intricate dance of the planets. Each of these facts paints a fuller, more serene, subtle processes and enduring cosmic mysteries. Continuing our gentle exploration, we find that Jupiter's atmosphere is home to ammonia ice clouds, which are primarily responsible for the planet's pale, light-coloured zones. These higher altitude clouds, composed of delicate ammonia crystals, softly reflect sunlight, creating the brighter, more ethereal bands that gracefully adorn Jupiter's vast gaseous sphere. They represent regions where warmer gases gently rise, bringing these icy compounds to the visible layers. In contrast, the darker belts, which alternate with these bright zones, are composed of ammonium hydrosulfide clouds. These clouds appear in deeper red-brown hues due to their chemical composition, absorbing more sunlight and residing at slightly lower altitudes within the atmosphere. The interplay between these distinct cloud layers, with their varying compositions and heights, creates the striking and intricate banded appearance that is so characteristic of the giant planet, a continuous, unhurried display of atmospheric artistry. The Great Red Spot, that iconic persistent feature, is understood to be a high-pressure anticyclonic storm. This means it rotates in a direction opposite to what is typically observed in a cyclone, a majestic atmospheric ballet that has endured for centuries. Scientists believe that the Great Red Spot may be slowly diminishing in size over long cosmic timescales, a gradual transformation within its immense structure, though its remarkable persistence, spanning at least 350 years, remains an intriguing cosmic mystery and a testament to the stability of Jupiter's atmospheric dynamics. Jupiter's stunning auroras, ethereal glows of light at its poles, are generated by charged particles gently flowing along its powerful magnetic field lines. These particles, originating from the solar wind and from Jupiter's volcanically active moon Io, are gracefully guided by the planet's immense magnetic field towards its polar regions. As these energetic particles softly collide with gases in Jupiter's upper atmosphere, they transfer energy, causing the atmospheric gases to emit light in serene shades of red and blue. These celestial light shows, far grander than any seen on Earth, create a breathtaking display of cosmic energy. The Juno spacecraft, currently in orbit around Jupiter, has provided unprecedented close-up views of Jupiter's polar auroras, revealing intricate and delicate patterns of light that continually dance across the high-latitude skies, offering new insights into these captivating phenomena. Jupiter's moon. Europa is considered a prime target for future missions seeking signs of life, due to its profound potential for harboring liquid water. Beneath its icy crust, scientists believe there lies a vast subsurface ocean, gently warmed by tidal forces, holding more water than all of Earth's oceans combined. This hidden aquatic realm makes Europa one of the most compelling locations in our solar system for astrobiological exploration. Future missions to Europa might involve highly specialized landers or even submersibles, meticulously designed to gently explore its subsurface ocean, quietly delving into its depths to search for any subtle signs of life. Such an endeavor would represent a patient and profound step in humanity's quest to understand life beyond Earth. The Moon. Io, in stark contrast to Europa's icy tranquility, is a world of continuous and intense geological activity. Io's volcanoes erupt plumes of sulfur and sulfur dioxide, which can gently reach heights of hundreds of miles above its surface, creating a dynamic and ever-changing landscape. This constant volcanic resurfacing, fueled by extreme tidal heating from Jupiter's immense gravitational pull, ensures that Io remains a world perpetually transforming under cosmic forces. Ganymede's magnetic field, a unique feature among solar system moons, is embedded within Jupiter's much larger magnetosphere, creating a complex interaction. This nesting of magnetic fields, where Ganymede's own magnetic bubble exists within Jupiter's colossal one, leads to intricate and subtle electromagnetic phenomena, a continuous interplay of cosmic forces. This unique characteristic adds another layer of complexity to Ganymede's already fascinating nature, making it a world of quiet magnetic wonders. Callisto's lack of significant internal heating, unlike its sister moons, suggests it has a simpler, less dynamic interior. This absence of strong tidal forces or primordial heat has allowed Callisto to remain a more placid and unchanging world, preserving its ancient, heavily cratered surface over billions of years. Its serene, stable interior offers a glimpse into a quieter form of cosmic evolution, a stark contrast to the dramatic activity seen on Io and Europa. Jupiter's powerful gravitational field has a subtle, yet measurable influence on the timing of our own planet's orbit around the Sun. This colossal gravitational presence causes minute perturbations in Earth's orbital path, a gentle, rhythmic tug that astronomers can precisely calculate. This subtle interaction highlights the interconnectedness of all bodies within the solar system, a continuous, unhurried gravitational dance. Furthermore, the planet's immense mass causes a subtle wobble in the Sun, a gentle motion that can be observed from afar. As Jupiter orbits, its gravitational pull causes the Sun to shift slightly off its exact center of mass. This quiet, rhythmic stellar movement is one of the primary methods exoplanet hunters use to detect other planets around distant stars, a clever application of gravitational principles to uncover hidden worlds. Jupiter's atmosphere contains a vast amount of hydrogen, making up about 90% of its composition by number of atoms. This overwhelming dominance of hydrogen, the universe's most abundant element, a direct link to the primordial building blocks of the cosmos. Helium constitutes about 10% of Jupiter's atmosphere, with all other elements such as methane, ammonia, and water vapor making up a tiny fraction. This simple, yet profound elemental makeup reflects the fundamental composition of the early solar system, a quiet testament to its ancient origins. Deep within Jupiter's core region, under such extreme pressure and immense temperatures, the hydrogen undergoes a remarkable transformation, becoming metallic. In this exotic state, it, flowing freely and conducting electricity with serene efficiency. The density of this liquid metallic hydrogen within Jupiter is so immense that a small cup of it, if somehow brought to Earth, would weigh many pounds, a testament to the colossal forces at play in the planet's interior. This profound density speaks volumes to the unique conditions that govern the heart of the gas giant, a silent, powerful realm. Jupiter's rapid rotation, completing a full turn in less than 10 hours, generates powerful Coriolis forces. These subtle yet pervasive forces subtly organize its vast atmospheric flows into the distinct, elegant bands that we observe, shaping the planet's iconic appearance. This continuous, unhurried motion creates a global pattern of atmospheric circulation, a cosmic ballet of gases. The planet's atmosphere is constantly changing, with new storms forming and old ones fading, creating a dynamic and ever-evolving weather system. This constant flux, a gentle dance of atmospheric forces, ensures that Jupiter's visible surface is perpetually transforming, a living, breathing canvas of cosmic weather. Some of Jupiter's smaller inner moons act as shepherd moons, gently influencing the particles within its delicate ring system. These tiny celestial bodies, through their subtle gravitational tugs, help to maintain the structure and definition of Jupiter's faint rings, a delicate cosmic choreography. Their presence ensures the rings do not disperse, but instead retain their ethereal form, a quiet interaction between moons and dust. The moon Europa's icy crust is believed to be relatively thin in some areas, potentially allowing for easier access to its vast subsurface ocean. This intriguing characteristic makes Europa an even more compelling target for future exploration, as a thinner crust could simplify the challenge of reaching its hidden aquatic depths. This subtle geological feature hints at a dynamic interaction between the surface and the ocean below, a continuous, gentle reshaping. Io's volcanoes are constantly active, making it the most geologically dynamic moon in our entire solar system. Its surface is perpetually being resurfaced by plumes of sulfur and sulfur dioxide, creating a vibrant, ever-changing landscape. This relentless activity, fueled by immense tidal forces, ensures that Io is a world of continuous transformation, a silent, powerful forge of new terrain. Ganymede's expansive surface features impact craters that are often surrounded by bright rays of ejected material, softly spreading across the icy landscape. These delicate patterns, created by the force of ancient impacts, offer clues to the moon's geological history and the composition of its icy crust. Callisto's surface, in contrast, is one of the darkest among the Galilean moons, absorbing more sunlight than its brighter companions. This darker hue is thought to be due to the presence of non-ice materials, possibly organic compounds or silicates, accumulated over billions of years, a quiet testament to its ancient placid nature. Jupiter's powerful magnetosphere, a vast and unseen force field, protects the planet and its inner moons from the harsh environment of the solar wind. This immense protective bubble deflects many harmful charged particles, creating a safer haven within its embrace, shielding these celestial bodies from the energetic onslaught of solar radiation. It is a silent, powerful guardian, ensuring a measure of calm within its sphere of influence. The Great Red Spot generates immense heat due to the friction and energy within the storm, gently warming the surrounding atmosphere. This internal warmth, born from the continuous swirling motion of gases, contributes to the storm's remarkable longevity and its role in Jupiter's overall atmospheric dynamics. This subtle thermal signature is another facet of the Great Red Spot's enduring mystery, a quiet testament to its internal power. Jupiter's internal heat source, which causes it to emit more energy than it receives from the Sun, suggests it is still slowly contracting, a gradual process that releases gravitational energy. This gentle, patient compression of its vast mass generates continuous warmth, contributing to the planet's dynamic internal processes and its overall thermal balance. This slow contraction is a silent, powerful engine driving many of Jupiter's most profound characteristics. The planet's strong magnetic field is thought to originate from the convection of liquid metallic hydrogen in its deep interior. This exotic conductive fluid, flowing under immense pressures and temperatures, acts like a colossal dynamo, patiently generating the magnetic field through its continuous, unhurried motion. This profound internal process creates the vast magnetosphere that envelops Jupiter, a silent, powerful force that shapes its cosmic environment. Each of these facts, woven together, paints an even richer and inviting us to delve deeper into its tranquil wonders. Jupiter's atmosphere has a very low water content in its upper layers, which for a long time made the presence of powerful lightning storms a fascinating puzzle for scientists. On Earth, lightning is strongly associated with water-rich clouds. However, the Juno mission has detected water vapor in deeper layers of Jupiter's atmosphere, supporting the idea of a water cycle beneath the visible cloud tops, where water ice and liquid water clouds exist, providing the necessary conditions for these colossal electrical discharges. This discovery quietly solved a long-standing atmospheric enigma. Jupiter's largest moon, Ganymede, holds a unique celestial characteristic. It is the only moon in the solar system to possess its own active magnetic field. This profound feature sets it apart from all other satellites, and even some planets. This magnetic field within Ganymede is thought to be generated by a convective liquid iron core, much like Earth's own internal dynamo. This dynamic, flowing iron creates a powerful, unseen shield around Ganymede, adding a layer of magnetic complexity to this already remarkable world, a silent, powerful force. The Munio's surface is constantly being reshaped by relentless volcanic eruptions, covering it in fresh layers of sulfur and silicate rock. This continuous geological activity ensures that Io's landscape is perpetually new, erasing older features and creating a vibrant, ever-changing tableau. Io's distinctive yellow, orange, and red colours, which make it a visually striking world, are primarily due to the presence of various sulfur compounds on its surface, gently deposited by its numerous volcanic plumes. These colours are a vivid testament to its intense internal heat and dynamic resurfacing. Europa's subsurface ocean, hidden beneath its icy shell, is estimated to be about 60 to 100 miles deep, a truly vast reservoir of liquid water. This immense, tranquil body of water, far deeper than any ocean on Earth, holds the tantalizing possibility of supporting simple forms of life, hidden beneath the ice, shielded from the harsh radiation of space. The sheer volume and protected nature of this deep ocean make Europa a prime candidate for astrobiological research, inspiring profound scientific curiosity about life beyond Earth. Jupiter's moon, Callisto, is considered geologically dead, meaning it lacks significant internal heat or activity. This characteristic offers a glimpse into a more serene cosmic past, a world that has largely remained unchanged since its formation. The ancient surface of Callisto acts as a cosmic archive, meticulously preserving a record of impacts from billions of years ago, a quiet testament to its placid geological history and a window into the early solar system. Jupiter's strong gravity significantly influences the distribution of dust and small particles throughout the outer solar system. Its colossal mass acts as a gravitational sculptor, gently guiding the paths of these minuscule remnants. The planet's presence likely contributed to the formation of the Kuiper Belt, a distant region of icy bodies beyond Neptune, by subtly shaping the movement and accumulation of material in that remote area. This profound gravitational influence underscores Jupiter's role in the grand architecture of our solar system, a silent, powerful force of cosmic organization. Scientists frequently use Jupiter's gravitational influence to perform gravity assist maneuvers for spacecraft, gently accelerating them on their long journeys across the solar system. By carefully swinging a probe close to Jupiter, its immense gravity provides a boost in speed and alters the spacecraft's trajectory. This clever technique allows spacecraft to conserve precious fuel and reach distant destinations more efficiently, a masterful and patient use of cosmic forces to aid human exploration. Jupiter's Great Red Spot is so vast that it could comfortably contain 2 or 3 Earth-sized planets within its swirling expanse. This colossal scale emphasizes the sheer magnitude of atmospheric phenomena on gas giants, dwarfing anything experienced on our home world. Its immense size is a constant reminder of Jupiter's grand proportions and the powerful, enduring forces at play within its atmosphere. Finally, the planet's atmosphere exhibits a phenomenon called prograde jets, where powerful winds flow consistently in the direction of Jupiter's rotation. These persistent currents, part of the planet's distinctive banded structure, contribute to the dynamic and colourful appearance of its cloud tops, a continuous, unhurried flow that shapes the majestic face of the gas giant. This harmonious movement is a fundamental aspect of Jupiter's complex atmospheric circulation. Jupiter's atmosphere also features retrograde opposite direction of the planet's rotation. This creates a complex interplay of forces with the prograde jets, contributing to the shearing and mixing that define Jupiter's dynamic weather system. This constant, unhurried opposition of atmospheric currents is a fundamental aspect of the gas giant's intricate banded appearance, a majestic and continuous atmospheric dance. The planet's powerful magnetic field causes charged particles to spiral gracefully around its field lines, creating radio emissions that are detectable from Earth. These invisible yet energetic streams of particles, moving in harmony with Jupiter's immense magnetic forces, generate powerful radio signals that can be captured by specialized instruments. This phenomenon offers a unique auditory window into the dynamic processes occurring within Jupiter's magnetosphere, allowing scientists to listen to the planet's energetic environment from vast distances. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are tidally locked to the planet, meaning the same side of each moon always faces Jupiter, much like Earth's own moon always presents the same face to us. This tidal locking is a gentle consequence of Jupiter's immense gravitational pull, exerted patiently over billions of years, slowly bringing the moons into synchronous rotation. This quiet celestial ballet ensures a consistent orientation for each moon as it orbits its colossal parent. Europa's icy shell is thought to be a dynamic layer, with subtle evidence of fractures, ridges, and chaotic terrain, suggesting ongoing activity beneath its frozen surface. These delicate patterns, visible across its exterior, hint at the movement and interaction of ice rafts and the upwelling of material from below, indicating a world that is quietly, yet persistently, reshaping itself. This dynamic icy crust is a key factor in the potential for a subsurface ocean to sustain life. The Moon Io's volcanic plumes can extend gracefully into space, creating a temporary atmosphere that is constantly replenished by its continuous eruptions. As volcanic gases and particles are ejected hundreds of miles above Io's surface, they form a transient gaseous envelope that is swiftly swept away by Jupiter's powerful magnetosphere, only to be replaced by the next eruption. This constant cycle of eruption and dispersal ensures Io remains a world of profound atmospheric renewal. Ganymede's expansive surface shows evidence of cryovolcanism in its past, where icy material may have erupted onto the surface, flowing like lava but composed of water and other volatiles. These ancient icy flows and structures hint at periods of internal heat and geological activity that gently reshaped Ganymede's crust, contributing to its diverse surface features. This quiet, ancient dynamism, Callisto's interior is believed to be a mixture of rock and ice that is not fully separated into distinct layers, unlike the other Galilean moons which show clear differentiation. This lack of complete layering suggests a quieter internal evolution, with less intense heating and geological activity over its history. This simpler interior structure is consistent with Callisto's ancient, heavily cratered surface, a world that has remained largely undisturbed for eons. Jupiter's immense size and mass make it a miniature solar system in itself, with its many moons orbiting around it in a complex and harmonious celestial dance. This vast collection of satellites, each a unique world, mimics the larger solar system structure, offering a captivating model for studying planetary systems. Its sheer gravitational dominance creates a stable environment for its diverse lunar family. The planet's gravitational pull has cleared a significant path in the asteroid belt, creating distinct gaps known as Kirkwood gaps. These gaps are regions where orbital resonances with Jupiter prevent asteroids from maintaining stable orbits, subtly sculpting the asteroid belt into its characteristic structure. Asteroids in these resonant orbits are either gently pushed out or pulled in, creating zones of depletion, a quiet testament to Jupiter's long-term influence on its cosmic neighbours. Jupiter's intense radiation environment, generated by charged particles trapped in its powerful magnetosphere, presents a significant hazard for human exploration. This pervasive high-energy radiation requires advanced shielding for any future missions, making close human proximity a profound challenge. Protecting spacecraft and astronauts from these powerful fields is a critical consideration for any long-duration presence near the giant planet. The planet's atmosphere experiences powerful lightning discharges that are thousands of times more energetic than Earth's lightning. These colossal electrical storms illuminate Jupiter's vast cloud layers with breathtaking flashes of light, a testament to the immense energy and dynamic processes occurring within its deep atmosphere. These powerful bursts of energy highlight the extreme conditions found on the gas giant, a spectacular display of cosmic power. Jupiter's rapid rotation creates a distinctive flattened shape, an oblate spheroid, due to the outward force at its equator. This centrifugal force, generated by its swift spin, causes the planet to bulge slightly at its middle and flatten at its poles, subtly altering its perfect spherical form. This characteristic shape is a direct visual consequence of its fast rotation, a quiet, enduring testament to its dynamic motion. Finally, the planet's rotation period is not uniform, with its equatorial regions spinning slightly faster than its polar regions. This differential rotation, where different latitudes move at different speeds, contributes to the complex wind patterns and the shearing forces that help create Jupiter's prominent atmospheric bands. This subtle variation in rotational speed is a key aspect of Jupiter's dynamic and ever-changing atmosphere, a continuous, unhurried flow of gases that shapes its majestic appearance. Jupiter's moon. Europa's vast subsurface ocean is thought to be in direct contact with a rocky seafloor, a crucial condition for potential hydrothermal activity. This intimate interaction between liquid water and rock could provide a steady supply of chemical energy for life forms, much like the deep-sea vents found on Earth's ocean floor. This tantalizing possibility makes Europa a prime candidate in the search for extraterrestrial life, suggesting a hidden, tranquil realm where biological processes might quietly unfold. Io's active volcanoes constantly release immense heat, a direct consequence of the Moon's relentless tidal flexing under Jupiter's powerful gravitational pull. This continuous internal warmth contributes significantly to the Moon's geological dynamism, fueling its hundreds of volcanoes and perpetually reshaping its vibrant surface. The steady escape of this internal energy is a testament to the profound forces at play within Io's core, a silent, powerful engine. Ganymede, the solar system's largest moon, possesses a global magnetic field that creates its own mini-magnetosphere. This unique magnetic bubble is gracefully nestled within Jupiter's much larger magnetosphere, forming a fascinating celestial anomaly. This intricate magnetic layering leads to complex interactions between the two fields, a subtle and powerful dance of cosmic forces that continually shape Ganymede's environment. Callisto's ancient surface is covered in a dark, non-ice material, a stark contrast to the brighter, icy exteriors of its sister moons. This dark coating is likely composed of organic compounds and silicates, accumulated over billions of years, acting as a quiet testament to the Moon's placid and largely undisturbed history. Its unique composition offers clues to the primordial materials present in the outer solar system. Jupiter's powerful magnetic field extends so far into space that it interacts with the magnetic field of the Sun, creating a complex and dynamic boundary. This colossal interplay of magnetic forces, stretching across vast interplanetary distances, forms a subtle yet powerful interface where the solar wind is gently deflected and shaped. This grand interaction highlights Jupiter's profound influence on the broader solar system environment, a silent, pervasive presence. The planet's atmosphere experiences subtle, wave-like phenomena, including gravity waves and acoustic waves, which quietly transport energy and momentum through its vast gaseous layers. These unseen ripples and undulations play a role in the complex dynamics of Jupiter's atmosphere, influencing cloud formation and the distribution of heat, a continuous, unhurried dance of atmospheric physics. Jupiter's cloud patterns are constantly evolving, providing a visually captivating and ever-changing display. New storms emerge, existing vortices shift and merge, and the distinct bands subtly alter their hues and widths, offering a continuous, majestic spectacle. This dynamic evolution ensures that Jupiter's appearance is never static, a living, breathing canvas of cosmic artistry. The Great Red Spot is a long-lived anticyclone, a testament to the remarkable stability of Jupiter's atmospheric dynamics over centuries. Its enduring presence, swirling in a counterclockwise direction, demonstrates the powerful yet harmonious balance of forces that sustain this colossal storm. This persistent atmospheric feature is a quiet symbol of Jupiter's enduring power and the long timescales over which cosmic processes unfold. Jupiter's internal structure is still an active area of research, with new models constantly being refined by mission data, particularly from the Juno spacecraft. Scientists are patiently working to unravel the precise composition and arrangement of its deep layers, from the exotic metallic hydrogen to its rocky core, continually deepening our understanding of this colossal world. Each new piece of data subtly enhances our cosmic knowledge. The planet's role as a bouncer or shepherd of the solar system is vital for maintaining its long-term stability. Guardian, gently deflecting potentially hazardous comets and asteroids away from the inner planets, ensuring a more stable and predictable environment for life to flourish on Earth. This silent, powerful influence safeguards the delicate balance of our planetary neighborhood. Jupiter's strong gravitational pull can even influence the trajectory of interstellar objects passing through our solar system. If a celestial wanderer from another star system happens to drift close enough, Jupiter's colossal mass can subtly alter its path, sending it on a new cosmic journey. This profound gravitational reach underscores Jupiter's role as a dominant force, even affecting visitors from beyond our Sun's domain. The planet's immense gravity played a key role in the early solar system, shaping the distribution of protoplanetary material. Its colossal mass helped to sculpt the nascent solar nebula, influencing where other planets formed and preventing material in the asteroid belt from fully coalescing. This early gravitational influence was fundamental in establishing the architectural blueprint of our current solar system, a silent, powerful act of cosmic creation. Jupiter's atmosphere contains powerful winds that can reach immense atmospheric currents, driven by the planet's internal heat and rapid rotation, create the distinct, colourful bands that characterize the giant planet's majestic appearance. These swift, unhurried flows are a visual testament to the colossal energy at play within Jupiter's dynamic atmosphere. Jupiter's magnetic field is the strongest planetary magnetic field in our solar system, a silent, powerful force that permeates vast regions of space. This immense magnetic shield, generated deep within its metallic hydrogen ocean, creates a protective bubble around the planet and its inner moons. The planet's vast magnetosphere is so large that if it were visible to the naked eye from Earth, it would appear several times larger than the full moon in Earth's sky, a breathtaking testament to its colossal scale and profound reach. Our serene journey concludes, leaving us with a deeper appreciation for the quiet power, subtle processes, and enduring cosmic mysteries of the majestic gas giant, Jupiter. And now, as the image of Jupiter's colossal invisible magnetosphere gently fades from our minds, our journey through its many wonders draws to a tranquil close. You have drifted through 100 quiet revelations, from the majestic, enduring swirl of the Great Red Spot to the hidden, potentially life-sustaining ocean beneath Europa's icy crust. We've explored the subtle dance of its powerful magnetic field, the vibrant, ever-changing patterns of its atmosphere, and the patient gravitational influence it exerts across our solar system. You are a part of this grand cosmic story, not merely an observer, but a participant, woven into the very fabric of stardust and time. The atoms that compose your being were forged in the distant ancient fires of stars, long before our sun came into its serene existence. The air you gently breathe carries the legacy of cosmic events, vast and unhurried. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through distant galaxies and drifts in interstellar clouds, a profound and peaceful connection. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming in distant nurseries, light is travelling across unimaginable expanses, and celestial dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars, cradled by the gentle rhythm of the universe. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.
Hello there, and welcome to Cosmos for Sleep. Tonight, we're embarking on a gentle journey through our own cosmic neighborhood, the solar system. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. The Sun accounts for 99.8% of the entire solar system's mass, dominating its gravitational pull. This central star, a radiant heart, holds everything within its vast gravitational embrace. Its immense presence shapes the orbits and movements of every planet, moon, and smaller body, orchestrating a silent, grand cosmic ballet. Without this singular, powerful influence, our familiar system would simply not exist in its current, harmonious form. This profound dominance of the Sun's mass is the very foundation upon which our solar system is built. It is this overwhelming gravitational field, an invisible yet undeniably potent force that acts as the unbreakable tether, binding all the planets, dwarf planets, asteroids, and comets into their graceful, predictable orbits. From the swift, rocky worlds closest to its warmth to the distant, icy realms far beyond Neptune, every single object within our cosmic home is intricately linked to the Sun's commanding pull. This deep gravitational connection is not a sudden, dramatic force, but a constant, pervasive presence, ensuring the harmonious order and enduring stability of our planetary neighborhood. The Sun's sheer bulk, representing nearly all the matter in the solar system, allows it to maintain this overarching control, a silent, powerful guardian presiding over our cosmic family. This immense concentration of mass at the center ensures that all other bodies revolve in a delicate equilibrium, a testament to the Sun's ultimate authority in this vast, tranquil expanse. The planets, in their patient journeys, are forever influenced by this colossal anchor, their paths woven into the fabric of the Sun's pervasive gravity, creating the serene, predictable rhythms we observe across billions of miles. It is a subtle, yet absolute form of cosmic governance, a gentle hand guiding the celestial dance. To truly appreciate the Sun's majestic grandeur, one must consider its staggering physical dimensions. 1 million Earths could comfortably fit inside the Sun, showcasing its immense size. Let us take a moment to gently imagine this colossal scale. Envision our familiar homeworld, with its swirling blue oceans, its verdant green continents, its towering mountain ranges, and its expansive, ever-changing skies. Now, try to picture a million such vibrant worlds, each unique and teeming with its own delicate ecosystems and intricate geographies, all nestled with ease within the embracing, gargantuan sphere of our star. This quiet thought experiment helps us to grasp the truly astounding physical dimensions of our Sun, a furnace of light and warmth that stretches beyond our everyday comprehension. Its vast, perfectly spherical form commands the absolute center of our solar system, a magnificent testament to the powerful, shaping forces of gravity that meticulously crafted it from a primordial cloud of gas and dust. This singular, expansive orb, so much grander and more voluminous than any planet orbiting it, provides an unwavering anchor, both visually and gravitationally, for all the celestial bodies that dance around it in their measured ancient paths. The very light that bathes our planet, sustaining all forms of life, originates from this immense radiant source, a constant, tranquil emanation streaming across the silent void, a timeless reminder of its majestic, enduring presence in the cosmic tapestry. Its sheer volume ensures that it remains the undisputed giant, effortlessly holding its court of planets in a perpetual, graceful waltz. Deep within this colossal, luminous star lies its fiery, energetic heart, a region of profound intensity where the Sun's core reaches astonishing temperatures of 15 million degrees Celsius. It is in this incredibly hot and dense central region that the sublime and powerful process of nuclear fusion takes place. Here, under conditions of unimaginable pressure and extreme thermal energy, hydrogen atoms are gently coaxed to combine or fuse, forming new atoms of helium. This delicate cosmic alchemy, occurring ceaselessly, releases an immense and continuous stream of energy, a steady, inner glow that powers our entire star. The conditions required for this intricate process are truly extraordinary, far exceeding anything we can replicate or even fully experience on Earth. Yet it is this stable, internal furnace that provides the boundless energy radiating outward, sustaining our entire solar system. This constant internal warmth is the very essence of the Sun's being. A perfectly stable engine humming softly and reliably at the heart of our cosmic home, ensuring its consistent output. The Sun's core is a realm of such profound activity that it shapes everything about the star, from its outward appearance to its life-giving warmth. It is a testament to the elegant yet powerful processes at play in the heart of a star, generating the very light and heat that allow our world to thrive. As a direct and awe-inspiring consequence of this ceaseless internal process, the Sun converts about 4 million tons of matter into energy every second through nuclear fusion. This staggering, almost incomprehensible rate of conversion is what perpetually fuels the Sun's brilliant luminosity and its constant, life-giving warmth. Each passing second, an almost imperceptible amount of its colossal mass transforms into pure, radiant energy, a gentle cascade of photons that streams outward across the boundless vacuum of space. This energy manifests as sunlight, a pervasive and comforting glow that travels patiently, bathing our planets in its vital warmth and illuminating their surfaces. This continuous process has been unfolding with unwavering consistency for billions of years, a testament to the Sun's enduring power and its central role as the primary energy source for all life on Earth. It is a profound demonstration of the universe's elegant and fundamental laws, where matter and energy are intertwined in a ceaseless, wondrous exchange, a constant cosmic alchemy that ensures the continuation of warmth and light throughout our planetary system. The gentle outflow of this converted energy is what allows plants to grow, oceans to warm, and life to flourish, a subtle yet mighty testament to the Sun's quiet generosity. Our Sun is scientifically classified as a G-type main sequence star, often referred to by astronomers as a yellow dwarf, though in truth, its actual light is perceived as white. The designation yellow dwarf can be a little misleading to the casual observer, as its inherent color, when viewed from the pristine vantage point of space, is a pure, brilliant white. It only appears with a yellowish tint to our eyes here on Earth due to the subtle filtering effects of our planet's atmosphere, which scatters blue light more effectively. Being a main sequence star signifies that our Sun is currently in the most stable and longest phase of its stellar existence. During this tranquil period, it steadily fuses hydrogen into helium within its deep core, maintaining a balanced and consistent energy output. This classification places it among a vast and numerous population of stars throughout the cosmos that are also in a similar, peaceful stage of their stellar evolution. This remarkable stability is a key factor in the long-term habitability of Earth, providing a reliable and consistent energy output that has nurtured life for billions of years. Its gentle, unwavering radiance is a steadfast beacon, patiently guiding and warming our entire solar system with an enduring and dependable consistency, a silent promise of continued illumination. The radiant energy that emanates from this brilliant white star embarks on an incredible and unhurried journey across the silent void of space. It takes light from the Sun approximately 8 minutes and 20 seconds to reach Earth. Despite light being the fastest entity known in the universe, traveling at an astonishing speed of approximately 299,792 kilometers per second, or 186,282 miles per second, The immense distance between the Sun and Earth means that this measured delay is always present. This fascinating cosmic lag means that when we gaze upon the Sun or feel its gentle warmth on our skin, we are not experiencing it exactly as it is in that very moment, but rather as it appeared a little over 8 minutes in the past. It is a subtle yet profound reminder of the vastness of space and the unhurried pace of cosmic communication. This constant, unceasing flow of light, traveling patiently and purposefully across millions of miles, is what illuminates our days, defines our seasons, and powers the delicate, intricate ecosystems of our world. Each photon, having begun its journey moments ago, brings with it the ancient story of the Sun's enduring light. Our steadfast and enduring Sun is estimated to be about 4.6 billion years old, marking it as a mature and venerable celestial body within the grand cosmic timescale. This significant age places it roughly halfway through its stable main sequence phase, the longest and most tranquil period of its life, where it consistently fuses hydrogen into helium in its core. This exceptionally long and patient lifetime provides a profound sense of cosmic continuity and reliability. For billions of years, the Sun has graced our solar system with its unwavering warmth and consistent light, serving as a constant, dependable presence in the unfolding cosmic drama. Scientists estimate it has another 5 billion years of stable burning ahead before it begins its gentle, gradual transformation. In the distant, far-off future, it will slowly expand into a red giant, gracefully shedding its outer layers to form a beautiful, ethereal planetary nebula, before eventually settling into a serene and compact white dwarf star. This long, predictable life cycle is a reassuring thought, a testament to the stable, enduring nature of our home star and the gentle, unhurried progression of cosmic time, a silent promise of billions more years of steady radiance before its final, graceful, cosmic change. As our Sun continues its patient, luminous journey, we turn our gaze inward towards the two closest planetary companions, Mercury and Venus, each a world of remarkable and often surprising characteristics. Among these inner rocky worlds, Venus presents a particularly fascinating rhythm. A day on Venus is longer than its year, taking 243 Earth days to rotate on its axis, but only 225 Earth days to complete a full orbit around the Sun. Imagine a world where the slow, deliberate turning of the planet means that the sunrise, once begun, would stretch across what feels like an eternity to our earthly senses, only to be followed by an equally prolonged and unhurried sunset. This exceptionally leisurely rotation creates a unique temporal experience, where the cycles of light and darkness unfold with an almost imperceptible slowness compared to our own planet's brisk 24-hour spin. The Sun, as viewed from the Venusian surface, would appear to crawl across the sky, taking many Earth months to traverse from one horizon to the other. This gentle, drawn-out celestial dance is a testament to the subtle gravitational and rotational forces that have shaped this planet over billions of years, creating a day that defies our intuitive understanding of planetary motion. The very concept of a Venusian day becomes a sprawling, patient epoch, a long, quiet passage of time that slowly unwinds as the planet makes its way around its solar parent. This extended period of rotation means that different regions of Venus are exposed to the Sun's direct radiance for prolonged durations, leading to particular atmospheric patterns that are unique to this world, further contributing to its distinctive character within our solar system. Adding to Venus's distinctiveness is its unusual rotational direction. Venus rotates clockwise, a retrograde motion, unlike most other planets in our solar system. While the majority of planets in our cosmic neighborhood spin in a counterclockwise direction, when viewed from above the Sun's north pole, Venus gracefully turns in the opposite manner. This peculiar backward spin sets it apart, a cosmic anomaly that has long intrigued astronomers. Scientists believe this unusual rotation might be the result of a colossal impact with another celestial body in its distant past, an ancient, gentle collision that subtly altered its rotational momentum. Alternatively, it could be a consequence of complex gravitational interactions with the Sun and other planets over vast timescales, slowly guiding it into this unique orientation. Regardless of its origin, this retrograde rotation contributes to the extended length of its day, as the planet's spin works against the direction of its orbital motion. The serene, unhurried turning of Venus in this reverse direction paints a picture of a world following its own quiet, independent path, a testament to the diverse and sometimes unexpected outcomes of cosmic evolution. This singular characteristic adds another layer of quiet mystery to our understanding of this cloud-shrouded neighbor, a planet that truly dances to its own measured, unhurried rhythm. The atmosphere of Venus is composed almost entirely of carbon dioxide, creating a runaway greenhouse effect that dramatically shapes its surface conditions. This incredibly dense and pervasive atmospheric blanket, far thicker than Earth's, acts like an insulating shield, effectively trapping the sun's warmth and preventing it from radiating back into space. The carbon dioxide molecules, abundant and tightly packed, absorb thermal energy with remarkable efficiency, leading to a relentless and extreme warming of the planet's surface. This constant, gentle accumulation of heat has transformed Venus into a world of intense, pervasive warmth, where the ground itself glows with a subtle, infernal heat. The delicate balance of energy that we experience on Earth, where some solar radiation is absorbed and some is reflected, is entirely absent on Venus. Instead, the heat is held captive, creating an environment that is consistently and profoundly warm across its entire landscape, untouched by the cooling breezes that might otherwise offer a momentary respite. This pervasive, heat-trapping effect is a powerful demonstration of how atmospheric composition can fundamentally alter a planet's climate, creating a world of quiet, enduring thermal intensity. Consequently, despite being farther from the Sun than Mercury, Venus is hotter than Mercury due to its thick, heat-trapping atmosphere. This might seem counterintuitive at first glance, as one would naturally expect the planet closest to the Sun to experience the most intense heat. However, Venus's dense carbon dioxide atmosphere completely alters this expectation. While Mercury, being the innermost planet, receives a greater direct intensity of solar radiation, it lacks a substantial atmosphere to retain that heat. Venus, on the other hand, with its potent greenhouse effect, effectively captures and holds on to the warmth it receives, accumulating it over time. The constant, tranquil embrace of its thick atmospheric blanket ensures that the surface temperature remains uniformly high, day and night, across the entire planet. This creates a pervasive, unyielding warmth that far surpasses even the scorching daytime temperatures of Mercury. It is a striking example of how a planet's atmospheric composition can be a more significant factor in determining its surface temperature than its mere proximity to its star, revealing a subtle complexity in the thermal dynamics of our solar system's inner worlds. The silent, efficient work of Venus's atmosphere transforms it into a gentle furnace, radiating a warmth that never truly dissipates. In stark contrast to the pervasive warmth of Venus, Mercury experiences the most extreme surface temperature variations in the solar system, from over 427 degrees Celsius during its prolonged day to a chilling minus 179 degrees Celsius at night. This astonishing temperature swing, spanning more than 600 degrees Celsius, creates a landscape of unparalleled thermal extremes. During the lengthy periods when one side of Mercury faces the Sun, it is bathed in an intense, unyielding solar radiance, causing its rocky surface to heat to incandescent levels, hot enough to melt lead. Yet, as the planet slowly rotates and that same surface turns away from the Sun, plunging into its equally prolonged night, the absence of atmospheric insulation allows the accumulated heat to rapidly dissipate into the cold vacuum of space. The transition from scorching day to frigid night is a dramatic testament to the planet's unique thermal environment, where the very rocks of its surface endure a constant, profound shift between intense heat and deep cold. This cosmic rhythm of extreme temperature changes creates a landscape that is both harsh and profoundly quiet, a world of silent, unceasing thermal flux, endlessly cycling between fiery warmth and icy stillness. The primary reason for Mercury's dramatic thermal shifts is that it has no atmosphere to trap heat, leading to its dramatic temperature swings. Unlike Earth's protective and insulating blanket of air, or Venus's thick, heat-retaining shroud of carbon dioxide, Mercury exists in an almost perfect vacuum. Any solar energy that reaches its surface is either absorbed or reflected, but very little is retained or redistributed. Without an atmospheric layer to circulate warmth from the sunlit side to the shadowed side, or to hold onto heat during the long nights, the planet's surface temperatures fluctuate wildly. The solar winds, unhindered by atmospheric resistance, directly interact with its exposed surface, creating a stark, unimpeded exchange of energy with the cosmos. This absence of an atmospheric buffer means that Mercury's surface is fully exposed to the harsh realities of space, experiencing the sun's direct, unfiltered radiance and the deep, pervasive cold of the vacuum with equal intensity. It is a world stripped bare, its naked surface patiently absorbing and releasing warmth in a continuous, unmediated cycle. This fundamental characteristic defines Mercury's thermal environment, making it a world of silent, extreme contrasts, a testament to the crucial role an atmosphere plays in moderating a planet's climate. A final shared characteristic between these two innermost worlds, Mercury and Venus, is that both lack natural moons, a distinction shared only by these two inner planets within our solar system. Unlike Earth, which is graced by its single luminous lunar companion, or the outer planets with their extensive retinues of diverse satellites, Mercury and Venus journey around the Sun in solitary splendor. This absence of natural moons contributes to their quiet isolation within the inner solar system, highlighting a subtle difference in their gravitational histories compared to our own planet. Scientists believe that this lack of moons might be due to their close proximity to the Sun, where the Sun's immense gravitational pull could have either prevented the formation of moons or stripped away any that might have formed in the distant past. It is also possible that any early moons may have simply merged with their parent planets over billions of years, a gentle, unhurried process of cosmic integration. This shared characteristic of being moonless worlds adds to their unique identities, painting a picture of two planets that navigate their orbital paths without the delicate gravitational dance of a celestial partner. They float serenely, quietly, and alone, a testament to the varied outcomes of planetary formation within our tranquil solar system. As these two innermost worlds complete their solitary orbits, our journey now turns to our own familiar blue sphere, Earth, and its steadfast companion, the Moon. Our home planet holds a unique distinction among its celestial neighbors. Earth is the only planet in our solar system not named after a Roman or Greek deity. While Mercury takes its name from the swift messenger god, and Venus from the goddess of love and beauty, Earth carries a name rooted in ancient Germanic languages, meaning simply ground or soil. This humble origin speaks to a profound connection to the very substance that forms our world, a grounding identity that sets it apart from the grand mythological pantheon. It is a name that quietly echoes its role as a foundation, a place of stable ground and nurturing soil, a haven for life in the vast expanse of space. This simple, earthy designation reflects the planet's essence, a place of tangible substance and sustained existence, a contrast to the ethereal, godlike names bestowed upon the other wandering stars in our sky. It reminds us of the quiet strength and enduring presence of our planetary home, a world defined by its tangible reality rather than by ancient tales. Our celestial companion, the Moon, maintains a subtle yet ceaseless dance with our planet, a relationship that is slowly, almost imperceptibly, evolving. The Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. This gradual recession, while seemingly small, adds up to significant distances over the immense stretches of cosmic time. It is a patient, unhurried process, driven by the intricate gravitational interactions between Earth and its moon. As the moon's gravity gently pulls on Earth's oceans, it creates tidal bulges. Earth, rotating beneath these bulges, experiences a gentle friction that transfers a tiny amount of rotational energy to the moon. In turn, this minuscule addition of energy causes the moon to spiral ever so slightly outward, gradually increasing its distance from us. This slow, elegant drift is a testament to the dynamic, ever-changing nature of celestial mechanics, where even the most stable relationships are subject to subtle, long-term shifts. Over millions and billions of years, this imperceptible outward movement has shaped the moon's orbit and influenced Earth's rotation, a quiet, continuous reshaping of our shared cosmic environment. It is a testament to the enduring, yet ever-evolving bond between our planet and its luminous satellite, a slow, patient unfolding of cosmic destiny. Deep within Earth's heart, a silent, powerful engine tirelessly works to protect all life on its surface. Earth's molten outer core generates a powerful magnetic field that protects us from solar radiation. This invisible shield, often referred to as the magnetosphere, is born from the gentle churning and convection of liquid iron within our planet's outer core, creating vast electric currents that extend far into space. Like a protective, ethereal cocoon, this magnetic field gracefully deflects harmful charged particles, primarily from the sun's constant outflow of solar wind and more energetic cosmic rays. Without this powerful, pervasive barrier, these high-energy particles would relentlessly bombard Earth's surface, stripping away our atmosphere and making life as we know it impossible. It is a quiet, yet utterly vital guardian, a constant, unseen embrace that safeguards our delicate biosphere. This intricate internal process ensures a stable and serene environment, allowing the gentle rhythms of life to flourish undisturbed by the harsh conditions of interstellar space. The magnetic field is a profound testament to Earth's self-sustaining mechanisms, a silent, enduring protector woven into the very fabric of our planet's being, ensuring a tranquil and safe harbor for all. This intimate gravitational connection with the moon also subtly influences our planet's own internal rhythm. The Earth's rotation is gradually slowing down, making days slightly longer over vast geological timescales. This unhurried deceleration is primarily a consequence of the moon's gravitational pull on Earth's oceans, creating the tides. The friction generated by the movement of these tidal bulges across the ocean floor acts as a gentle brake on Earth's rotation. While the effect is incredibly subtle, amounting to only a few milliseconds per century, it is a persistent force that has profoundly shaped Earth's rotational period over billions of years. In the distant past, Earth's days were significantly shorter, perhaps as little as 6 hours long. This gradual, patient lengthening of our days is an ongoing, imperceptible process, a testament to the enduring gravitational dialogue between Earth and its lunar companion. It is a slow, rhythmic adjustment, a quiet rebalancing of angular momentum that unfolds with an almost majestic slowness, weaving the cosmic dance into the very fabric of our planet's temporal cycles. This steady, unhurried change is a quiet reminder of the deep, interconnected nature of our solar system. Our moon, often perceived as a simple orb in the night sky, holds a remarkably prominent place among the solar system's satellites. Our moon is the 5th largest moon in the solar system and is unusually large compared to its parent planet. While many planets host numerous moons, few possess a satellite of such significant relative size. To put its scale into perspective, the moon's diameter is more than 1/4 that of Earth, a proportion rarely seen in other planetary systems. This unusual grandeur is believed by scientists to be the result of a colossal impact event in the early solar system, where a Mars-sized body gently collided with a nascent Earth, gradually coalescing to form our majestic companion. This theory suggests a singular, profound birth for our moon, one that endowed it with its remarkable size and stable orbit. Its substantial presence exerts a powerful gravitational influence on Earth, acting as a stabilizing force on our planet's axial tilt, which in turn contributes to the relatively stable climate patterns that have allowed life to flourish. This unusually large and significant lunar presence is not merely a distant light, but an integral part of Earth's cosmic identity, a quiet, enduring partner in our planetary journey. The most tangible and immediate evidence of this enduring partnership is found in the rhythmic pulse of our planet's oceans. The moon's gravitational pull creates ocean tides on Earth, a subtle dance between celestial bodies. As the moon orbits our planet, its gravitational force gently tugs at Earth's water, creating bulges on both the side of Earth facing the moon and on the opposite side. Our planet then rotates through these bulges, leading to the familiar ebb and flow of high and low tides that grace our coastlines twice each day. This ceaseless, rhythmic motion of the waters is a direct, observable consequence of the moon's pervasive gravitational presence, a silent and ancient dialogue between two celestial bodies. It is a testament to the moon's enduring influence, shaping the very edges of our continents and stirring the vast depths of our seas. This constant, unhurried cycle of rising and falling waters highlights the delicate balance of forces at play, a harmonious interaction that has sculpted coastlines and influenced marine life for billions of years, a tranquil, predictable rhythm in the grand cosmic symphony. Finally, enveloping our world in a protective, life-sustaining embrace is the very air we breathe. Earth's atmosphere is a delicate blend of nitrogen, oxygen, argon, and other gases vital for life. This translucent, ethereal blanket, extending hundreds of miles above the surface, is a finely tuned composition that has allowed complex life to emerge and thrive. Nitrogen, making up about 78%, acts as a gentle diluent, moderating the reactivity of oxygen. Oxygen, at around 21%, is the essential gas that fuels respiration for countless organisms. Argon and a trace of other noble gases, along with water vapor and carbon dioxide, complete this intricate mixture. Beyond providing the necessary gases for breathing, the atmosphere also acts as a thermal regulator, gently trapping some of the sun's warmth to maintain a habitable temperature range, preventing the extreme fluctuations seen on moonless, airless worlds. It also serves as a protective shield, gently incinerating incoming meteoroids before they can reach the surface. This serene and complex atmospheric veil is a testament to Earth's unique planetary conditions, a delicate, vital embrace that cradles and sustains all forms of life, a quiet, breathing presence that defines our habitable home in the vastness of space. From the life-sustaining embrace of Earth's atmosphere, our celestial journey now extends outward to our intriguing neighbor, Mars, often known as the Red Planet. Mars holds a truly awe-inspiring geological marvel. Olympus Mons on Mars is the highest mountain and largest volcano in the solar system, standing 3 times taller than Mount Everest. Imagine a vast, shield-shaped mountain, so immense that its gentle slopes would barely be perceptible from its base, stretching across a region larger than the state of Arizona. This colossal dormant volcano rises majestically from the Martian plains, its summit piercing the thin atmosphere to an elevation of over 21 kilometers or 13 miles. Its sheer scale is a quiet testament to a past era of profound geological activity on Mars. When immense plumes of molten rock slowly erupted and accumulated over billions of years, building this monumental structure, the low gravity on Mars, combined with the absence of shifting tectonic plates, like those on Earth, allowed volcanic flows to continuously build upon themselves, culminating in this singular, breathtaking peak. Olympus Mons stands as a silent sentinel, a majestic, ancient monument to the powerful, shaping forces that have gently sculpted the Martian landscape over cosmic time, a testament to the planet's grand and unhurried geological history. Its presence suggests a world that once experienced a very different, yet equally serene, internal dynamism, slowly crafting this unparalleled landmark that remains one of the most iconic features in our solar system. The sheer volume of material that formed this mountain speaks to an enduring, patient process of planetary formation and evolution, where gravity and internal heat worked in quiet concert to create such an immense and captivating structure. Beyond its towering peaks, geological evidence reveals a vastly different past for the red planet. Scientists believe that Mars once had liquid water flowing on its surface and a much thicker atmosphere, as evidenced by geological features. Gentle, winding river valleys, ancient lake beds, and mineral deposits that typically form in the presence of water are quietly etched across the Martian landscape, telling a story of a warmer, wetter world billions of years ago. These subtle geological imprints suggest a time when Mars might have harbored a more Earth-like environment, where water flowed freely, perhaps even supporting a primitive form of life. The presence of a thicker atmosphere would have been crucial, providing the necessary pressure and insulation to keep liquid water stable on the surface, preventing it from boiling away into space or freezing solid. Over vast stretches of cosmic time, however, Mars gradually lost much of its atmosphere to the relentless solar wind, a gentle stripping away of its protective veil. This loss led to a gradual cooling and drying of the planet, transforming it into the cold, arid world we observe today. The ancient riverbeds and dried-up lake beds stand as silent reminders of this profound planetary transformation, whispering tales of a long-lost watery past, a testament to the slow, unhurried evolution of a planet that once held the promise of liquid oceans. This quiet, geological record allows us to peek into a bygone era, understanding how even familiar planets can undergo dramatic yet serene shifts in their environmental conditions, highlighting the subtle dance of atmospheric escape and solar influence. Further out in its orbital embrace, Mars is accompanied by two small, irregularly shaped moons, Phobos and Deimos, which are thought to be captured asteroids. These two diminutive celestial bodies are not spherical like Earth's moon, but rather resemble potatoes, with uneven surfaces and numerous craters. Their irregular forms and close orbits suggest that they did not form alongside Mars from the same primordial disk of material, but were instead gravitationally snared by the red planet's pull sometime in the distant past. As they drifted too close to Mars, perhaps on a leisurely journey through the asteroid belt, the planet's gravity gently guided them into stable, albeit eccentric orbits. Phobos, the larger and closer of the two, is slowly spiraling inward and is predicted to either gently break apart or merge with Mars in about 50 million years, a slow, unhurried end to its cosmic dance. Deimos, the smaller and more distant moon, maintains a more stable, yet equally patient, orbit. These two quiet, captured companions offer astronomers valuable insights into the gravitational dynamics of planetary systems and the processes by which celestial bodies can be subtly drawn into new cosmic relationships, adding to the quiet complexity of our solar system's architecture. Their presence is a testament to the enduring, subtle gravitational forces that constantly reshape and reconfigure the smaller elements within our cosmic neighborhood. The most striking visual characteristic of this planet, and the source of its popular moniker, is its distinct red color. The distinct red color of Mars comes from iron oxide, or rust, in its soil. This pervasive reddish hue, visible even from Earth, is not merely a superficial coating, but an integral part of the Martian regolith, the loose surface material that covers the planet. Billions of years of exposure to oxygen, likely released from past water or atmospheric processes, cause the iron-rich rocks and dust to slowly oxidize, creating vast expanses of rust-colored terrain. This subtle chemical transformation, unfolding with an unhurried grace over eons, has painted the entire planet in shades of ochre, crimson, and burnt orange, giving it its iconic appearance. The dust, suspended in its thin atmosphere, further scatters this reddish light, lending the Martian sky a soft, salmon pink glow. This quiet, chemical process has profoundly shaped the visual identity of Mars, making it a uniquely captivating world in our night sky, a testament to the slow, patient interactions between planetary geology and atmospheric chemistry, creating a landscape that is both beautiful and profoundly serene in its coloration. Despite its stark differences from Earth, Mars exhibits a familiar rhythm in its celestial mechanics. Seasonal changes on Mars are similar to Earth's, with polar ice caps that grow and shrink. Just like our home planet, Mars is tilted on its axis, leading to different regions receiving varying amounts of sunlight throughout its orbit around the Sun. This axial tilt, similar in angle to Earth's, results in distinct Martian seasons, each unfolding with a quiet predictability. During the Martian winter, the polar ice caps, composed of both water ice and frozen carbon dioxide, expand significantly, gently accumulating layers of frost. As spring arrives and summer progresses in each hemisphere, these brilliant white caps slowly recede, releasing carbon dioxide back into the atmosphere and subtly altering atmospheric pressure. This seasonal dance of expansion and contraction is a mesmerizing display of planetary meteorology, a slow, patient exchange of volatiles between the surface and the atmosphere. It highlights a common thread in the orbital mechanics of our solar system, where axial tilt plays a crucial role in shaping the environmental cycles of planets, creating a beautiful, unhurried ballet of ice and atmosphere that unfolds across the Martian landscape, a distant echo of Earth's own seasonal rhythms. Looking towards the future, Mars continues to hold a profound allure for humanity. Future human missions to Mars are being planned, aiming to establish a presence on another planet. Scientists and space agencies across the globe are diligently working on developing the technologies, strategies, and infrastructure necessary to transport astronauts to the Red Planet, sustain them there, and eventually return them safely to Earth. These ambitious plans envision a gentle expansion of human presence beyond our home world, a patient and measured step towards becoming a multiplanetary species. Establishing a sustained human presence on Mars could involve building habitats, developing methods for resource utilization, and conducting long-term scientific research that deepens our understanding of planetary evolution and the potential for life beyond Earth. This quiet, purposeful endeavor is driven by a deep human curiosity and an enduring desire to explore, to reach out and touch another world. The meticulous planning and gradual technological advancements represent a slow, deliberate unfolding of humanity's cosmic aspirations, a testament to our gentle yet persistent drive to expand our horizons and establish new footholds in the vast, serene expanse of our solar system, preparing for a future where humanity might softly tread upon the red dust of another world. As we gently drift past Mars, our cosmic journey leads us to a fascinating and often misunderstood region of our solar system, the asteroid belt. The asteroid belt, located between the orbits of Mars and Jupiter, is vast, but individual asteroids are typically millions of miles apart, not densely packed. When depicted in films or popular media, this cosmic neighborhood is often shown as a chaotic, densely crowded field of tumbling rocks, making perilous passage for any spacecraft. In reality, the asteroid belt is an immense, sprawling expanse of space, so expansive that the average distance between any two sizable asteroids is millions of kilometers. This means that navigating through the belt is far from a dangerous obstacle course. A spacecraft can traverse it with relative ease, encountering very few objects along its path. The sheer volume of space within the belt, combined with the relatively small size of most asteroids, ensures that these remnants of the early solar system maintain a respectful and peaceful distance from one another. This tranquil, unhurried separation allows each asteroid to follow its own gentle orbital path without frequent, dramatic encounters. It is a testament to the quiet order that prevails even in regions of concentrated cosmic debris, where the vastness of space ensures a serene, uncrowded journey for any silent explorer. The impression of a chaotic jumble is replaced by a vision of a subtle, dispersed collection of ancient cosmic building blocks, each patiently tracing its own long elliptical route around our central star. Within this expansive, thinly populated belt resides its most significant inhabitant, Ceres. The largest object in the asteroid belt is also classified as a dwarf planet. Unlike the irregularly shaped asteroids that surround it, Ceres is massive enough for its own gravity to have gently pulled it into a nearly spherical form, a defining characteristic of a dwarf planet. This celestial body, with a diameter of about 940 kilometers, or 585 miles, holds a unique position, bridging the gap between the smaller, more numerous asteroids and the larger, more prominent planets. Scientists believe that Ceres possesses a differentiated interior, meaning it has distinct layers, possibly including a rocky core and a mantle of water ice, perhaps even with a subsurface ocean. The presence of water ice is particularly intriguing, as it offers clues about the distribution of volatiles in the early solar system and the potential for chemical processes. Ceres orbits the Sun quietly and steadily, a tranquil, luminous presence within the asteroid belt, a testament to the diverse forms that celestial bodies can take in our cosmic neighborhood. Its classification as a dwarf planet highlights its substantial nature and its importance as a unique world in its own right, a serene and ancient body that patiently reveals the subtle complexities of planetary evolution. These numerous smaller bodies that populate the belt are, in essence, cosmic fossils. Asteroids are rocky, airless remnants from the early formation of our solar system. These diverse objects, ranging in size from tiny pebbles to hundreds of kilometers across, represent the primordial building blocks that never quite coalesced into a full-fledged planet. Approximately 4.6 billion years ago, as our solar system was slowly taking shape from a swirling cloud of gas and dust, these rocky fragments were left behind, unable to fully combine due to the immense gravitational influence of the nearby giant planet Jupiter. Instead of forming a single large planet, they remained scattered, patiently orbiting the Sun in their designated region. Each asteroid carries within its stony composition the chemical signatures of that ancient era, offering scientists invaluable insights into the conditions and materials present during the birth of our planetary system. They are silent witnesses to the turbulent yet creative processes of cosmic formation, small, enduring pieces of a grander, unfolding story. These airless wanderers, each a unique fragment of cosmic history, continue their unhurried journey, preserving the subtle echoes of creation in their weathered surfaces, a tranquil reminder of the solar system's formative years. Despite the vast numbers of individual asteroids, their collective mass is surprisingly modest. The total mass of the asteroid belt is less than the mass of Earth's moon. This fact often comes as a quiet revelation, especially given the common perception of a crowded, substantial belt. If one were to gather all the asteroids, large and small, and combine them into a single celestial body, its mass would still be less than that of our familiar lunar companion. This relatively low total mass indicates that the asteroid belt is primarily composed of smaller fragments, and that a significant amount of material that might have formed a planet was either ejected from the solar system or incorporated into other bodies during the early, more chaotic stages of formation. The gravitational dominance of Jupiter played a crucial role in preventing these scattered remnants from fully coalescing, gently stirring the region and preventing the formation of a larger, unified planet. This subtle, yet profound gravitational influence ensured that the material remained dispersed, a collection of smaller, individual pieces, rather than a singular, massive world. The asteroid belt, therefore, is a quiet, sparsely populated region, a testament to the elegant gravitational forces that shape the distribution of matter in our solar system, revealing a delicate balance of cosmic influences. The visual appearance of most asteroids further distinguishes them from the larger, more familiar planets. Many asteroids are not spherical, but have irregular shapes due to their relatively small size and weak gravity. Unlike planets and dwarf planets, which possess sufficient mass for their own gravity to pull them into a rounded, hydrostatic equilibrium, the majority of asteroids are simply too small to achieve this spherical form. Their gravitational fields are relatively weak, unable to overcome the internal strength of their rocky structures. As a result, they retain the irregular, jagged, or elongated shapes they acquired during their formation or from subsequent, gentle collisions. These diverse and often peculiar forms are a quiet testament to their unique histories, each lump and crater telling a silent story of ancient impacts and unhurried cosmic weathering. From elongated peanut-like shapes formed by two smaller asteroids gently merging, to fragmented, angular boulders, each asteroid presents a distinct silhouette against the backdrop of space. This characteristic shape, a direct consequence of their modest size, offers a visual cue to their status as remnants rather than fully formed planetary bodies. A peaceful collection of cosmic oddities, each patiently reflecting the subtle interplay of forces that shaped its individual form. Beyond their scientific value as cosmic relics, some asteroids hold a practical promise for future endeavors. Some asteroids contain valuable resources like metals and water ice. These celestial resources, locked within the rocky and icy compositions of these ancient bodies, represent a potential treasure trove for future space exploration and human expansion. Water ice, in particular, is an invaluable commodity. It can be melted for drinking, used as propellant for rockets when separated into hydrogen and oxygen, or utilized for life support systems. Metals like nickel, iron, and platinum group elements, which are rare on Earth's surface, are thought to be abundant in certain types of asteroids. The gentle extraction of these resources could eventually support long-duration missions to Mars or the establishment of orbital habitats, reducing the need to launch all materials from Earth. This quiet, potential wealth drifting through the asteroid belt offers a glimpse into a future where humanity might gently and responsibly harvest extraterrestrial resources, extending our reach into the solar system. The presence of these latent resources imbues these otherwise unassuming rocks with a profound potential, silently holding the promise of future cosmic ventures and the steady, unhurried. Among the many thousands of asteroids, one stands out as a beacon of visibility. The Vesta asteroid is bright enough to be seen from Earth with binoculars under ideal conditions. This remarkable visibility makes Vesta a unique and accessible object for amateur astronomers, offering a quiet connection to the distant asteroid belt. Vesta is the second most massive object in the asteroid belt, after the dwarf planet Ceres, and is distinguished by its relatively bright surface. Scientists believe that Vesta's surface is covered with basaltic rock, similar to the volcanic plains on Earth's moon, which reflects sunlight efficiently. Unlike many other asteroids, Vesta also shows signs of past volcanic activity and a differentiated interior, suggesting it was once a protoplanet that experienced internal heating. Its substantial size and reflective surface combine to make it a luminous point of light in the night sky, a patient, enduring presence that can be glimpsed from our own planet. This gentle visibility allows us to appreciate the subtle diversity within the asteroid belt, providing a tangible link to these ancient remnants of our solar system's formation, a quiet, luminous invitation to gaze outward and appreciate the serene complexity of our cosmic neighborhood. As we depart the tranquil, dispersed realm of the asteroid belt, our journey continues outward, leading us to the majestic presence of Jupiter, the undisputed monarch of our solar system. This colossal gas giant immediately captures attention with its most iconic and enduring feature. Jupiter's Great Red Spot is an enormous storm, wider than Earth, that has raged for at least 350 years, possibly much longer. Imagine a vast oval-shaped vortex, a serene crimson eye constantly swirling in Jupiter's southern hemisphere, a storm of such immense scale that our entire home planet could easily be swallowed within its gentle atmospheric embrace. This monumental anticyclone, observed for centuries by patient astronomers, represents a persistent, powerful atmospheric phenomenon, driven by the planet's internal heat and rapid rotation. Its continuous existence for such an extended period is a quiet testament to the enduring dynamics of Jupiter's turbulent yet stable atmosphere, where powerful currents and temperature differentials create these majestic, long-lived weather systems. The gentle, unhurried churn of this colossal storm, a silent ballet of atmospheric forces, paints a picture of a world where grand meteorological events unfold with a timeless, unwavering consistency, offering a profound glimpse into the powerful, yet serene, atmospheric processes of a gas giant. The Great Red Spot is not a fleeting tempest, but an ancient, patient force, a permanent fixture on Jupiter's ever-changing, cloud-banded face, a testament to its enduring power and the subtle, persistent nature of its atmospheric currents. Its quiet, persistent swirl reminds us of the profound timescales over which cosmic phenomena can unfold, a majestic, enduring feature that has captivated observers for generations. Jupiter's imposing presence is not merely visual, it dominates our solar system by its sheer scale. Jupiter is the largest planet in the solar system, with a mass 2.5 times greater than all other planets combined. This staggering statistic underscores its unparalleled gravitational authority and its central role in the architecture of our planetary system. Imagine gathering all the other planets, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and placing them on an immense cosmic scale. Jupiter alone would outweigh them all by a significant margin, a true giant among giants. This immense mass is predominantly composed of hydrogen and helium, remnants of the primordial cloud from which our solar system was born, gently compressed into a vast, swirling sphere under its own colossal gravity. Its profound gravitational influence extends far beyond its immediate vicinity, subtly affecting the orbits and movements of countless asteroids and comets throughout the outer solar system. This colossal size and mass make Jupiter a powerful gravitational anchor, second only to the Sun itself, orchestrating the delicate dance of its moons and shaping the paths of smaller celestial bodies. It is a quiet, dominant force, a majestic celestial body whose very existence profoundly influences the dynamics and stability of our entire cosmic neighborhood, a serene, powerful presence that commands respect. Among Jupiter's extensive retinue of 79 confirmed moons, one stands out as a prime candidate in the search for extraterrestrial life. Europa, one of Jupiter's 4 largest moons, is believed to harbor a vast subsurface ocean of liquid water, making it a prime candidate for extraterrestrial life. The evidence for this hidden ocean comes from subtle observations. The moon's fractured, icy surface, which shows signs of recent geological activity, and its weak magnetic field, which suggests the presence of a salty, conductive liquid beneath the ice. Scientists believe this ocean, potentially twice the volume of all Earth's oceans combined, is kept liquid by gentle tidal heating, a subtle warming caused by the constant gravitational tug-of-war between Europa, Jupiter, and its other large moons. This internal warmth could provide the necessary energy for chemical processes, potentially supporting microbial life in the deep, dark waters beneath the ice. The prospect of an alien ocean, shielded from the harsh radiation of space by miles of ice, presents a tantalizing possibility for astrobiological exploration. Europa floats serenely in Jupiter's immense gravitational field, a quiet, icy world holding a profound secret beneath its tranquil, frozen crust. A silent promise of potential discovery that continues to inspire wonder and scientific inquiry. Another of Jupiter's captivating large moons, Io, presents a dramatically different, yet equally active, face to the cosmos. Io, another of Jupiter's major moons, is the most volcanically active body in the solar system, constantly resurfacing itself. Unlike Europa's hidden ocean, Io's activity is expressed through a continuous, gentle outpouring of molten rock and sulfurous gases from hundreds of active volcanoes. This intense volcanism is driven by extreme tidal heating, a much more powerful version of the forces at play on Europa. Io is caught in a relentless gravitational tug-of-war between Jupiter and its other large moons, Europa and Ganymede. This constant squeezing and stretching of Io's interior generates immense frictional heat, melting its rocky interior and forcing magma to the surface. The result is a perpetually changing landscape where ancient craters are quickly buried under fresh lava flows, and towering plumes of volcanic material gently erupt into space, sometimes reaching hundreds of kilometers high. Io's vibrant, colorful surface, painted with shades of yellow, orange, and red from sulfur compounds, is a visual testament to this ceaseless geological dynamism, a world of quiet, persistent transformation. This moon is a powerful example of how gravitational forces can profoundly shape the geological evolution of a celestial body, creating a world of unhurried, yet intense, internal activity. Despite its immense size and powerful gravitational influence, Jupiter also possesses a subtle, ethereal adornment. Jupiter has a faint ring system, much less prominent than Saturn's, composed of tiny dust particles. Unlike the dazzling broad rings of its neighbor Saturn, Jupiter's rings are dark, tenuous, and composed mainly of microscopic dust grains gently shed from its inner moons as they are subtly bombarded by micrometeoroids. These delicate rings are virtually invisible from Earth without specialized telescopes and are best observed when illuminated from behind by the sun, revealing their ethereal glow. The ring system consists of 4 main components: a thick inner torus, known as the halo ring, a brighter main ring, and 2 fainter, broader outer gossamer rings, named after the moons Adrastea and Thebe, which are believed to be their source. The particles within these rings are constantly being created and dispersed, a quiet, dynamic process of replenishment and loss. Jupiter's rings offer a subtle reminder that ring systems are not exclusive to Saturn, but are a more common feature among the gas giants, each unique in its composition and visibility, a gentle, almost imperceptible whisper of cosmic dust circling the colossal planet. The sheer scale of Jupiter is closely linked to another of its defining characteristics. Jupiter's rapid rotation, completing a day in just under 10 hours, causes its distinctive flattened shape at the poles. While all planets bulge slightly at their equators due to centrifugal force from rotation, Jupiter's immense size and incredibly swift spin amplify this effect dramatically. Imagine a vast, fluid sphere spinning at such a dizzying speed that its middle gently swells outward, while its top and bottom appear slightly compressed. This subtle, yet measurable, oblateness is a direct consequence of the powerful rotational forces at play, creating a visible distortion in its otherwise perfectly spherical form. This rapid rotation also drives the powerful atmospheric currents that create Jupiter's iconic cloud bands and long-lived storms, including the Great Red Spot. The swift internal motions, combined with its gaseous composition, allow the planet to respond dynamically to these forces, creating a world that is constantly, subtly, reshaping itself with each passing rotation. It is a quiet testament to the interplay of mass, rotation, and fluid dynamics on a grand planetary scale, a majestic, unhurried spin that sculpts the very form of this gas giant. Finally, Jupiter's immense mass and powerful gravity play a crucial protective role for the inner solar system. Jupiter's immense gravity helps protect the inner solar system by deflecting or capturing comets and asteroids. Its colossal gravitational field acts as a cosmic broom, gently sweeping up or altering the trajectories of numerous smaller celestial bodies that might otherwise pose a threat to the inner rocky planets, including Earth. Many comets originating from the distant Oort cloud or Kuiper belt as they journey inward are either gently nudged onto new, safer paths by Jupiter's gravitational influence, or are captured into orbits around the gas giant itself. Some even meet their quiet end by colliding with Jupiter, leaving temporary scars on its cloud tops, a testament to its protective role. This continuous, unhurried process has been unfolding for billions of years, a silent guardianship that has profoundly shaped the environment of the inner solar system, reducing the frequency of potentially catastrophic impacts. Jupiter, the serene giant, acts as a benevolent protector. Its vast gravitational presence a constant, reassuring shield, silently ensuring a more stable and tranquil existence for the worlds nestled closer to the Sun. From Jupiter's benevolent guardianship, our quiet voyage now leads us to Saturn, the breathtaking jewel of our solar system, famed for its ethereal ring system. Saturn's iconic rings are composed of billions of individual pieces of ice and rock, ranging from microscopic dust to mountain-sized chunks. Imagine a vast, shimmering halo, a celestial masterpiece woven from countless fragments, each patiently orbiting the giant planet. These countless individual particles, from the tiniest motes of cosmic dust, no larger than grains of sand, to majestic chunks of ice and rock, some as substantial as small mountains, all contribute to the ring's luminous beauty. They drift in delicate harmony, a gentle, unhurried ballet around their gas giant parent, reflecting the sun's distant light with a serene, almost otherworldly glow. This intricate composition, a grand collection of icy debris, reveals the rings not as solid structures, but as a dynamic, ever-changing tapestry of countless small worlds, each following its own precise path. The sheer number of these individual pieces, numbering in the billions, creates an illusion of breathtaking solidity from a distance. Yet up close, they reveal a profound and subtle complexity, a quiet, continuous dance of cosmic fragments that endlessly reconfigure themselves. This delicate, shimmering expanse is a testament to the patient, persistent forces that shape such grand celestial phenomena, a timeless, elegant adornment that defines Saturn's majestic presence in our cosmic neighborhood. The ceaseless, silent motion of these particles, each a tiny world unto itself, ensures the enduring brilliance of Saturn's signature feature, a testament to the elegant processes that resolve into such breathtaking beauty. Their existence speaks to an ancient, ongoing process of formation and interaction, creating a vast, shimmering disk that captivates all who gaze upon it with a sense of quiet wonder. Among Saturn's numerous companions, one moon presents a particularly intriguing mystery, a world quietly whispering secrets from its depths. Enceladus, a moon of Saturn, has geysers erupting water vapor and ice particles from its south pole, hinting at a subsurface liquid ocean. Imagine delicate, luminous plumes of icy material, gently streaming into the profound darkness of space from subtle fissures near the moon's southern regions, a constant, quiet exhalation from within its frozen shell. These persistent geysers, observed with careful precision by visiting spacecraft, are powerful indicators of an active interior, suggesting that beneath Enceladus's bright, icy crust lies a vast, tranquil reservoir of liquid water. Scientists believe this hidden ocean, potentially warmed by internal geological processes and subtle tidal heating from Saturn's immense gravitational embrace, could provide an environment conducive to the emergence of microbial life. The water vapor and ice particles, carrying traces of salts and organic molecules, are like whispering messengers from this veiled aquatic realm, offering tantalizing clues about the chemistry and potential habitability of this enigmatic moon. Enceladus orbits Saturn with serene grace, a small yet profoundly active world, its gentle eruptions a silent invitation to explore the secrets hidden beneath its tranquil, frozen exterior. This continuous, unhurried release of material into space creates a delicate, ethereal halo around the moon, a subtle signature of the deep, liquid world concealed within, revealing a quiet, persistent dynamism that profoundly shapes its interaction with the broader cosmos. The prospect of such an ocean, a tranquil liquid world shielded by miles of ice, is a source of immense wonder and careful scientific exploration, a quiet beacon in the serene search for life beyond Earth. Moving further through Saturn's system, we encounter another moon of extraordinary character, a world cloaked in a perpetual, hazy beauty. Titan, Saturn's largest moon, is the only moon in the solar system with a dense atmosphere and stable bodies of liquid on its surface, albeit liquid methane and ethane. Unlike the watery oceans of Earth or the subsurface seas of Europa and Enceladus, Titan presents a world where the familiar cycles of precipitation and evaporation involve hydrocarbons. Its thick, hazy orange atmosphere, composed primarily of nitrogen with a significant amount of methane, creates a planetary environment that resembles a primordial Earth, albeit at much colder temperatures. Through this dense atmospheric veil, patient spacecraft have peered down to discover vast, tranquil lakes and meandering rivers of liquid methane and ethane, patiently flowing across its frigid landscape. These liquid bodies, sometimes calm and reflective under the distant sunlight, sometimes gently rippled by subtle winds, form a unique hydrological cycle, complete with clouds and rain, creating a world that is eerily familiar yet profoundly alien in its elemental composition. Titan orbits Saturn as a truly distinct celestial body, a serene world unto itself, its dense atmosphere and liquid surfaces painting a picture of patient, ongoing geological and atmospheric processes. This moon stands as a testament to the diverse and surprising forms that planetary environments can take. A quiet, orange-hued world where familiar processes unfold with profoundly different materials, revealing the serene and varied possibilities of cosmic chemistry. Its unique character makes it a captivating destination for future, gentle explorations, a world that quietly holds its own secrets within its veiled, hydrocarbon-rich embrace, an enduring enigma. Returning our attention to the planet itself, Saturn holds a surprising characteristic that sets it apart from its planetary peers, a fact that speaks to its ethereal composition. Saturn is the least dense planet in our solar system. It would float if placed in a sufficiently large body of water. Imagine a bathtub vast enough to hold a planet. Saturn, with its immense gaseous composition primarily of hydrogen and helium, is so diffuse that its average density is less than that of water. This remarkable lightness, despite its enormous size, highlights its fundamentally gaseous nature. Unlike the rocky terrestrial planets, or even the denser core regions of Jupiter, Saturn's bulk is predominantly made up of the lightest elements, gently compressed but never solidifying into a heavy, compact core in the same way. This ethereal, almost weightless quality contributes to its serene appearance, its swirling cloud bands seemingly weightless as they drift across its vast expanse. This quiet fact underscores the distinct differences between the rocky inner planets and the gaseous outer giants, revealing how the materials and conditions during their formation led to such varied outcomes. Saturn's low density is a testament to the delicate balance of matter and gravity, a unique and tranquil characteristic that makes it a true anomaly among its planetary siblings. A gentle giant that defies expectations with its inherent lightness and almost imperceptible mass for its size. Further enhancing its regal status, Saturn presides over an extraordinarily numerous celestial court, a vast and diverse family of companions. Saturn has over 83 confirmed moons, the most of any planet in our solar system. This vast retinue of natural satellites, a diverse collection of icy worlds, rocky fragments, and captured celestial bodies, creates a complex and dynamic miniature system around the ringed planet. From the large geologically active moons like Titan and Enceladus, to countless smaller, irregularly shaped ice chunks and shepherd moons that sculpt the rings, each moon follows its own patient orbital path. Influenced by Saturn's immense gravitational pull and the subtle interactions with its fellow satellites. This extensive family of moons is a testament to Saturn's powerful gravitational reach, which has gently gathered and held these celestial companions in its embrace over billions of years. Each moon, in its own quiet way, contributes to the intricate gravitational dance around the planet, shaping the rings, influencing other moons, and offering unique insights into the formation and evolution of planetary systems. This teeming celestial family, constantly in motion, creates a harmonious, complex ballet, a silent and enduring testament to the rich tapestry of our solar system's outer reaches, revealing the serene and multifaceted nature of planetary companionship, a truly majestic collection of worlds. Despite their immense scale and visual prominence, Saturn's rings possess an astonishing characteristic when viewed from a different perspective, one that speaks to their delicate structure. The rings of Saturn are surprisingly thin, typically only about 20 meters thick, despite their vast diameter. Imagine a vast, ethereal disk stretching hundreds of thousands of kilometers across, wide enough to comfortably contain several Earths, or even the distance from Earth to the Moon. Yet vertically, it is no thicker than a small house or a few stories of a building. This incredible flatness is a testament to the gentle, patient gravitational forces and the countless, subtle collisions that have shaped the ring particles over billions of years, gradually settling them into a remarkably narrow plane. The constant, unhurried interactions between billions of icy fragments, each gently nudging its neighbors, have effectively ironed out any vertical irregularities, creating a structure that is almost two-dimensional in its elegant simplicity. This delicate, paper-thin veil, so breathtakingly wide, yet so remarkably shallow, underscores the intricate and subtle dynamics at play within the ring system. It is a quiet marvel of celestial mechanics, a testament to the enduring power of gentle, repetitive interactions to create a structure of such profound beauty and astonishing slenderness, a truly unique and serene feature in the cosmic landscape, a delicate whisper of cosmic architecture that continues to mesmerize. Finally, within the intricate tapestry of Saturn's rings, one prominent feature highlights the subtle gravitational ballet at play, a clear pathway carved by an unseen hand. The Cassini division, a prominent gap in Saturn's rings, is cleared by the gravitational influence of the moon Mimas. This wide, dark band, easily visible even with small telescopes from Earth, is not an empty void, but a region where ring particles are significantly sparser. Its existence is a direct result of a gentle, persistent gravitational resonance with Mimas, one of Saturn's inner moons. As Mimas orbits, its gravity subtly tugs on any ring particles that would normally occupy the Cassini division. These particles, experiencing a repeated gravitational pull at specific points in their orbits, are gradually nudged out of the region, creating a clear pathway, a serene, empty channel in the otherwise dense ring system. This elegant gravitational interaction, a quiet and patient dance between a moon and countless ring particles, beautifully illustrates how even small celestial bodies can profoundly shape the larger structures around them. The Cassini division is a visible testament to the intricate, long-term gravitational dynamics that sculpt the delicate patterns within Saturn's rings, a silent, enduring monument to the subtle, powerful forces that orchestrate the celestial ballet, revealing the profound interconnectedness of Saturn's vast and beautiful system. It is a quiet reminder that even apparent emptiness can be a result of unseen, yet powerful cosmic forces, a testament to the gentle sculpting power of gravity. As we journey beyond the magnificent rings of Saturn, our cosmic path leads us to the serene, distant realms of the ice giants, Uranus and Neptune. These two ethereal blue worlds, shrouded in cold, hazy atmospheres, hold their own unique wonders and mysteries. Uranus, in particular, presents a truly exceptional orientation in its cosmic ballet. Uranus orbits the Sun on its side, with an axial tilt of 98 degrees, possibly due to an ancient collision. Imagine a planet gently rolling through space, rather than spinning upright like a top. This profound tilt means that its poles experience incredibly long periods of continuous daylight, followed by equally prolonged stretches of complete darkness, each lasting for decades. For nearly half of its 84-year orbital period, one pole faces the Sun, bathed in its distant, steady light, while the other remains in the quiet shadow of night. Then, as it continues its patient journey, the roles subtly reverse. Scientists believe this peculiar orientation, so different from the gentle upright spins of most other planets, is the lasting legacy of a colossal, yet ancient and unhurried impact with another large celestial body in the early solar system. This gentle, formative collision, occurring billions of years ago, would have subtly nudged Uranus onto its side, forever altering its rotational axis. The event, though grand in scale, would have unfolded over immense timescales, a slow reorientation that left its enduring mark. This unique axial tilt creates a world of extreme, yet predictable, seasonal variations, where the very concept of day and night unfolds in a majestic, drawn-out rhythm, a testament to the powerful shaping forces that have quietly sculpted our solar system's distant, blue-green giant. Its serene, sideways roll is a quiet anomaly, a constant reminder of the subtle, yet profound events that shape the planets into their current, distinctive forms. Further into the quiet outer reaches of our solar system, Neptune, the furthest major planet, showcases an astonishing atmospheric dynamism. Neptune boasts the fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour, or 1,200 miles per hour. Imagine atmospheric currents flowing at speeds that far exceed any hurricane or typhoon ever recorded on Earth. A relentless, powerful circulation sweeping across the entire planet. These incredible wind speeds, driven by Neptune's internal heat and rapid rotation, create a turbulent yet stable atmosphere where vast storm systems can form and persist. The planet's deep, cold interior and its gaseous composition allow for these powerful currents to develop with unhindered momentum, creating a dynamic weather system that is both awe-inspiring and profoundly serene. Despite their immense velocity, these winds contribute to the gentle, unhurried flow of Neptune's atmospheric bands, painting a picture of a world where powerful forces operate within a grand, majestic equilibrium. These rapid, sweeping currents play a crucial role in distributing heat and shaping the planet's appearance, ensuring a constant, quiet churn in its ethereal blue clouds. The sheer power of these atmospheric flows is a testament to the internal energy and fluid dynamics of this distant ice giant, a silent, powerful force shaping its character. Among Neptune's tranquil retinue of moons, one stands out with a particularly unique orbital characteristic. Triton, Neptune's largest moon, orbits in a retrograde direction, opposite to Neptune's rotation, and is likely a captured Kuiper Belt object. While most moons in our solar system orbit their parent planets in the same direction that the planet spins, Triton moves in a serene, counter-rotating path. This unusual backward orbit is a strong indicator that Triton did not form alongside Neptune from the same primordial disk of material. Instead, scientists believe that Triton was once an independent dwarf planet, slowly journeying through the distant Kuiper Belt, before being gently snared by Neptune's immense gravitational pull sometime in the distant past. This ancient, unhurried capture would have been a gradual process, subtly altering Triton's trajectory and guiding it into its current, stable, yet retrograde, orbit. The gravitational forces involved in this capture would have also generated significant internal heating within Triton, contributing to its geological activity, which includes subtle, icy geysers. Triton, with its unique backward dance, offers a quiet glimpse into the dynamic history of our solar system, a testament to the gentle gravitational forces that can reshape the destinies of celestial bodies, drawing them into new, enduring relationships within the vast, serene cosmic tapestry. Its peculiar orbit is a silent echo of a momentous, yet peaceful, past event, a constant reminder of the subtle, powerful hand of gravity. Observing Uranus from afar, its distinct coloration is one of its most recognizable features, a calm, captivating hue. Uranus's atmosphere contains methane, which absorbs red light and gives the planet its distinctive blue-green hue. The planet's upper atmosphere is rich in this simple hydrocarbon, which acts as a natural filter, gently absorbing the red and orange wavelengths of sunlight. The remaining blue and green light is then scattered back into space, creating the serene, uniform blue-green appearance that characterizes this distant world. Unlike the more complex, banded atmospheres of Jupiter and Saturn, Uranus's atmosphere appears remarkably smooth and featureless, a testament to its colder temperatures and deeper, less active cloud layers. This tranquil, consistent coloration is a direct result of its atmospheric composition, a delicate interplay of light and gas that paints the planet in soothing, cool tones. It is a quiet, visual signature of Uranus's unique atmospheric chemistry, a constant, gentle glow that defines its presence among the ice giants. This subtle interaction of light with its gaseous envelope creates a truly placid and uniform appearance, a serene expanse of blue-green that invites a sense of quiet contemplation. Neighboring Neptune, while also blue, exhibits a slightly different, more vibrant shade, a subtle distinction that reveals further atmospheric complexities. Neptune's vibrant blue color is attributed to methane in its atmosphere, absorbing red light more effectively than Uranus's atmosphere. While both ice giants owe their blue coloration to the presence of methane, Neptune's blue appears richer, deeper, and more intense. This difference is believed to be due to a slightly higher concentration of methane in Neptune's upper atmosphere, or perhaps to the presence of an unknown, additional atmospheric component that enhances the absorption of red light. This subtle difference in atmospheric chemistry creates a more profound and captivating shade of blue, a visual testament to the gentle variations that can exist even between seemingly similar planetary bodies. The deep, pervasive blue of Neptune evokes a sense of serene mystery, a world cloaked in a tranquil, almost oceanic hue that reflects its distant, cold environment. It is a quiet, yet striking visual characteristic that sets Neptune apart, painting it as a jewel of the outer solar system, its color a gentle whisper of the intricate atmospheric processes unfolding deep within its gaseous embrace. This visual elegance is a constant source of wonder, a calm, deep blue that permeates its entire visible surface. These two distant worlds share a fundamental classification that distinguishes them from their larger, more gaseous brethren. Both Uranus and Neptune are classified as ice giants, composed primarily of heavier elements like oxygen, carbon, nitrogen, and sulfur in their interiors. Unlike Jupiter and Saturn, which are predominantly made of hydrogen and helium, Uranus and Neptune possess a greater proportion of these ices, which, at the extreme pressures and temperatures deep within their interiors, exist not as solid frozen blocks, but as a superpressurized fluid slush. This unique internal composition means they have a relatively small rocky core surrounded by a vast fluid mantle of water, methane, and ammonia, often referred to as a supercritical fluid or ice layer. This distinct internal structure sets them apart from the gas giants and profoundly influences their atmospheric dynamics, magnetic fields, and overall evolution. The classification as ice giants emphasizes their unique chemical makeup, which is a gentle echo of the conditions present in the outer regions of the early solar nebula, where these heavier volatile compounds were more abundant. It is a quiet testament to the diverse pathways of planetary formation, showcasing a different kind of colossal world, one dominated by a deep, fluid ocean of exotic, dense ice that patiently defines their majestic, yet enigmatic, interiors. Finally, Neptune, like its larger neighbor Jupiter, also exhibits dynamic atmospheric phenomena, though with its own distinct rhythm. Neptune has a great dark spot, a storm similar to Jupiter's Great Red Spot, though it appears and dissipates over shorter timescales. Imagine a vast, oval-shaped atmospheric vortex, a temporary dark blemish on Neptune's vibrant blue surface, a powerful storm system swirling with high-speed winds. These immense anticyclones, akin to Jupiter's enduring Great Red Spot, are grand atmospheric features driven by the planet's internal heat and rapid rotation. However, unlike Jupiter's centuries-old storm, Neptune's great dark spots are more transient, gracefully forming, evolving, and then gently fading away over a period of several years. This more ephemeral nature suggests differences in the internal dynamics and atmospheric stability between the two ice giants. The appearance and dissipation of these dark spots are a quiet testament to the ever-changing, yet serene, atmospheric processes at play on Neptune, revealing a world of dynamic, unhurried meteorological shifts. Each spot, a temporary masterpiece of atmospheric forces, emerges and dissolves with a patient, rhythmic grace, highlighting the fluid and ever-evolving nature of this distant blue world, a testament to the subtle, powerful forces that continuously sculpt its atmospheric face. These gentle, transient storms are a captivating feature of Neptune, silently demonstrating the planet's profound atmospheric dynamism. As we journey beyond the swirling atmospheres of the ice giants, our cosmic exploration carries us into the colder, more distant reaches of our solar system. A realm populated by dwarf planets and a vast collection of icy remnants. Here, we encounter Pluto, a world that has long captured our collective imagination, yet whose true scale often surprises. Pluto is smaller than the United States, with a diameter of about 2,376 kilometers, or 1,473 miles. Imagine comparing the entire expanse of a country, stretching across a continent with its diverse landscapes and bustling cities, to the serene, icy sphere of this distant world. Pluto's modest size, while still significant for a celestial body, means it is considerably smaller than any of the major planets. Its surface, a tranquil tapestry of nitrogen ice plains, towering water ice mountains, and subtle reddish haze, unfolds over an area that would fit neatly within the boundaries of a single large nation on Earth. This quiet revelation about its true dimensions helps us to appreciate the delicate scale of this icy dwarf planet, a world that, despite its small stature, holds a profound beauty and geological complexity. Pluto drifts patiently at the edge of the familiar solar system, a small, yet captivating world that has slowly revealed its intricate features to distant probes. Its size is a testament to the diversity of celestial bodies, reminding us that even the smaller worlds can possess immense scientific interest and quiet majesty, a serene presence in the outer realms. Pluto is not alone in this distant, icy frontier. It is merely one of many objects residing in a much larger, sprawling cosmic neighborhood. The Kuiper Belt is a vast region beyond Neptune containing billions of icy bodies, remnants from the solar system's formation. Imagine a colossal, flattened disk stretching far beyond the orbit of Neptune, populated by a countless multitude of frozen worlds, from small icy pebbles to dwarf planets hundreds of kilometers across. This expansive, tranquil reservoir of ancient material represents the leftover building blocks from the early, unhurried formation of our solar system, approximately 4.6 billion years ago. These icy bodies, composed of water, methane, and ammonia ices, have remained largely undisturbed in their distant orbits, preserving the pristine conditions of the primordial solar nebula. The Kuiper Belt is a silent, frozen archive, a cosmic time capsule holding invaluable clues about the early history and composition of our planetary system. Its vastness and the sheer number of its inhabitants speak to the immense scale of the early solar system and the gentle, patient processes that shaped its distant reaches. Each icy body within this tranquil belt follows its own long, elliptical path, a quiet, enduring presence in the profound cold and darkness, a testament to the enduring nature of cosmic remnants, patiently awaiting discovery and study. The reclassification of Pluto in 2006 was a pivotal moment in our understanding of these distant worlds. Pluto was reclassified as a dwarf planet in 2006, leading to a new understanding of planetary definitions. For decades, Pluto held the esteemed title of the ninth planet, a solitary outpost at the solar system's edge. However, as astronomers discovered more and more large, icy bodies within the Kuiper Belt, some comparable in size or even larger than Pluto, the need for a clearer definition of planet became apparent. The International Astronomical Union, after careful deliberation, established 3 criteria for a celestial body to be considered a planet. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a nearly round shape, and it must have cleared its orbital neighborhood of other debris. Pluto, while meeting the first 2 criteria, did not meet the third, as it shares its orbital path with many other Kuiper Belt objects. This gentle reclassification was not a demotion, but rather an elevation of understanding, acknowledging Pluto as the prototype of a new class of celestial bodies, dwarf planets. This subtle shift in terminology reflects a more nuanced appreciation of the diverse and complex populations of our solar system, a quiet evolution in our cosmic vocabulary. It reminds us that our scientific understanding is ever evolving, patiently refining our definitions as new discoveries gently expand our knowledge of the universe. Indeed, the discovery of other substantial bodies in the Kuiper Belt directly influenced this reclassification. Eris, another dwarf planet in the Kuiper Belt, is slightly more massive than Pluto. When Eris was discovered in 2005, its estimated size and mass, initially thought to be larger than Pluto's, presented a challenge to the existing planetary definition. This finding was a key catalyst in prompting astronomers to re-evaluate what truly constitutes a planet. Eris, like Pluto, is an icy world, patiently orbiting the Sun in the distant reaches of the Kuiper Belt, far beyond Neptune. Its slightly greater mass, despite its similar composition, underscored the need for a more precise and consistent framework for classifying celestial objects. The quiet presence of Eris, subtly challenging our preconceived notions, led to a more comprehensive and inclusive understanding of the diverse populations of our solar system. It is a testament to the continuous process of scientific discovery, where new observations gently refine our models and deepen our appreciation for the vast, serene complexity of the cosmos. Eris, a distant, icy world, stands as a quiet symbol of this evolving understanding, a crucial piece in the ongoing cosmic puzzle, patiently revealing the subtle intricacies of planetary formation and classification. Among the intriguing dwarf planets of the Kuiper Belt, one exhibits a particularly distinctive form. Haumea, a dwarf planet, is notable for its elongated shape and rapid rotation, causing it to flatten. Unlike the perfectly spherical forms we often associate with celestial bodies, Haumea presents a more oblate, almost football-like appearance. This unusual shape is a direct consequence of its remarkably swift spin. Haumea completes a full rotation in just under 4 hours, making it one of the fastest rotating large objects in the solar system. This rapid, gentle pirouette creates a powerful centrifugal force that subtly stretches the dwarf planet along its equator and flattens its poles, preventing it from settling into a perfectly round shape despite its substantial mass. Scientists believe that this rapid rotation, and potentially its elongated form, might be the result of a past, gentle collision with another object in the early Kuiper Belt, an ancient, unhurried impact that spun it into its current, distinctive state. Haumea, with its unique and elegant form, is a quiet testament to the diverse and sometimes surprising outcomes of planetary evolution, where the interplay of gravity, rotation, and ancient impacts can sculpt celestial bodies into truly singular shapes. Its rapid, yet serene spin is a constant subtle force that maintains its elongated silhouette, a unique and captivating presence in the distant, icy reaches of our solar system. Another captivating resident of this distant realm is Makemake, a dwarf planet and one of the largest Kuiper Belt objects, known for its reddish-brown color. This subtle yet distinct hue sets Makemake apart, painting it with a unique visual signature against the backdrop of the cold, dark outer solar system. Scientists believe its reddish-brown coloration is likely due to the presence of complex organic molecules, or tholins, on its surface. These tholins are formed when ultraviolet radiation from the sun gently interacts with methane and other simple organic compounds on the dwarf planet's icy crust, slowly transforming them into more complex, reddish substances. This subtle chemical process unfolding patiently over billions of years in the profound cold and vacuum of space, has gradually imbued Makemake with its characteristic color. It is a quiet testament to the pervasive influence of solar radiation, even at such immense distances, and the gentle, persistent chemical transformations that can occur on icy worlds. Makemake drifts serenely through the Kuiper Belt, a silent reddish beacon, its unique coloration offering clues about its surface composition and the subtle chemical evolution of distant icy bodies. Its quiet, enduring presence adds another layer of intrigue to the diverse tapestry of dwarf planets, each revealing its own gentle, unique character. Beyond the dwarf planets themselves, the Kuiper Belt holds a profound significance for understanding the origins of some of our solar system's more ephemeral visitors. The Kuiper Belt is thought to be the source of many short-period comets that visit the inner solar system. Imagine a vast icy nursery, a tranquil reservoir from which these luminous wanderers occasionally emerge. Short-period comets are those that complete an orbit around the Sun in less than 200 years, making relatively frequent visits to the inner solar system. Scientists believe that gravitational perturbations, perhaps from the subtle tug of the giant planets or gentle collisions with other Kuiper Belt objects, can occasionally nudge these icy bodies out of their stable, distant orbits. Once disturbed, they begin a slow, unhurried journey inward, gradually warming as they approach the Sun and developing their characteristic glowing comas and tails. This quiet, continuous replenishment of comets from the Kuiper Belt highlights its enduring role as a dynamic, yet serene, source of celestial visitors, offering a tangible link between the distant, frozen reaches of our solar system and the warmer, more active inner regions. It is a testament to the subtle, patient gravitational forces that orchestrate the long, graceful journeys of these icy travelers, a continuous, quiet dance across vast cosmic distances. Adding another layer of complexity to this distant realm, some Kuiper Belt objects have their own moons, such as Pluto's 5 moons, including Charon. This fascinating characteristic demonstrates that the formation of satellite systems is not exclusive to the major planets, but can also occur around smaller, icy dwarf planets. Pluto, with its remarkable family of 5 known moons, Charon, Styx, Nix, Kerberos, and Hydra, offers a particularly rich example of a dwarf planet system. Charon, Pluto's largest moon, is so substantial in size relative to Pluto that the two are often considered a binary system, orbiting a common center of mass that lies between them. The formation of these moons around Kuiper Belt objects is believed to involve similar processes to those that formed larger planetary moons, such as ancient, gentle collisions or gravitational capture events in the early solar system. These miniature satellite systems provide invaluable insights into the gravitational dynamics and evolutionary pathways of distant, icy worlds. The quiet, intricate dance of these moons around their dwarf planet parents adds a profound sense of scale and complexity to the outer solar system, revealing that even in the most distant and seemingly desolate regions, the serene ballet of celestial companionship and gravitational interaction continues to unfold with elegant precision, a testament to the diverse ways in which cosmic structures can form and evolve. From Pi, our expedition now extends even further, pushing the boundaries of what we traditionally consider our solar system into realms of profound distance and subtle influence. Here, in the outermost reaches, lies a vast, spherical domain of icy remnants. The Oort cloud, the outermost region of our solar system, is thought to extend up to 100,000 astronomical units from the Sun, nearly a quarter of the way to the nearest star. To truly grasp this immense scale, consider that 1 astronomical unit, or AU, represents the average distance between Earth and the Sun, approximately 150 million kilometers, or 93 million miles. Now, multiply that by 100,000. This sprawling, ethereal shell of icy debris forms the true frontier of our planetary system, a profound expanse that defines the limits of the Sun's primary gravitational dominion. It is a region so vast and so distant that it almost touches the interstellar medium, the subtle gas and dust that permeate the space between stars. Imagine this immense, tranquil sphere, a cosmic halo surrounding our familiar inner worlds, stretching so far that the light from our sun becomes a mere faint pinprick, a distant, gentle star among countless others. Within this profound darkness, countless icy bodies drift in silent, unhurried orbits, patiently tracing paths that take thousands, even millions of years to complete. This unfathomable distance ensures a serene, almost imperceptible existence for these icy fragments, each a quiet relic from the very beginnings of our solar system, patiently suspended in the deep cosmic chill. The Oort cloud represents a truly grand and majestic boundary, a testament to the expansive reach of our sun's gentle influence, a serene transition from our home system into the vast, silent sea of interstellar space, a quiet, enduring whisper of our cosmic address. This distant, icy reservoir holds a profound significance for the occasional celestial visitors that grace our inner skies. The Oort cloud is believed to be the origin of long-period comets, taking thousands of years to orbit the Sun. Picture this immense primordial cloud as a vast spherical nursery, a tranquil haven for billions of icy bodies, each a pristine remnant cometary nuclei composed of water ice. Frozen gases and dust patiently reside in their distant orbits, largely undisturbed for billions of years. However, every so often, a subtle gravitational nudge, perhaps from a passing star or the gentle pervasive tug of the Milky Way galaxy itself, will delicately alter the trajectory of one of these icy wanderers. This gentle perturbation can cause a comet to begin an unhurried, millennia-long journey inward, gradually spiraling towards the warmth and light of our Sun. As these long-period comets make their rare and majestic appearances in the inner solar system, they offer us a fleeting, luminous glimpse into the composition of the Oort cloud and the conditions of the early solar nebula. Their incredibly elongated orbits, stretching for thousands of years, are a testament to the profound distances they traverse and the patient, unhurried pace of their cosmic dance. Each luminous visitor is a quiet messenger from the deep, dark fringes of our solar system, carrying with it the ancient story of its distant, icy home, a serene reminder of the subtle forces that guide these celestial wanderers. Yet, before we even reach the theoretical limits of the Oort cloud, our solar system is enveloped and protected by another vital, invisible structure. The heliosphere is a protective bubble of solar wind that envelops our solar system, shielding it from harmful interstellar radiation. Imagine an immense, ethereal cocoon, patiently inflated and maintained by the constant outflow of charged particles from our Sun, known as the solar wind. This gentle yet powerful stream of plasma flows outward in all directions, creating a vast magnetic bubble that extends far beyond the orbits of the planets. This pervasive, unseen shield acts as a crucial guardian, deflecting the more energetic and potentially damaging cosmic rays and interstellar gas that permeate the space between stars. Without the heliosphere's constant, tranquil embrace, our solar system would be directly exposed to the harsher environment of the galaxy, a reality that would profoundly alter the conditions for life within our planetary system. It is a testament to the Sun's enduring influence, extending its protective reach far into space, creating a serene and stable environment for its planetary family. This invisible, yet undeniably potent boundary quietly defines the true extent of the Sun's immediate atmospheric and magnetic dominion, ensuring a peaceful, sheltered journey for our entire system through the vast interstellar sea. The heliosphere is a silent, enduring testament to the subtle, yet profound, protective power of our star. The outer edge of this protective bubble forms a critical boundary, a subtle, defining line in the cosmic tapestry. The heliopause is the boundary where the solar wind meets the interstellar medium, marking the edge of the heliosphere. Visualize this not as a solid wall, but as a gentle, yet firm, invisible frontier, where the outflowing solar wind, which has expanded and slowed over billions of miles, finally encounters the diffuse gas and magnetic fields of interstellar space. It is a delicate transition zone, a region where the influence of our sun's constant stellar breeze gradually fades, giving way to the subtle, pervasive presence of the wider galaxy. This quiet meeting point is a dynamic region, constantly shifting and subtly responding to the varying pressures of both the solar wind and the interstellar medium. It represents the farthest reach of the sun's direct active influence, a profound threshold that marks our solar system's gentle departure from its home star's immediate embrace into the broader, more expansive environment of our Milky Way galaxy. The heliopause is a silent, enduring testament to the boundary between two distinct cosmic domains, a serene, invisible line in the cosmic sand that separates the familiar from the truly alien, a patient, unhurried transition into the vast unknown. In a monumental achievement of human ingenuity and patience, two pioneering spacecraft have quietly traversed this profound boundary. The Voyager 1 and 2 spacecraft have both crossed the heliopause, venturing into interstellar space. Launched in the late 1970s, these two enduring probes embarked on an unhurried, decades-long journey, silently carrying instruments that meticulously measured their surroundings. After traveling for over 35 years, Voyager 1, followed later by Voyager 2, gently pierced the heliopause, sending back data that confirmed their quiet departure from the sun's direct influence. This unprecedented crossing marked humanity's first tangible foray into the true interstellar medium, the vast, serene emptiness between stars. These silent messengers, now billions of miles from Earth, continue their patient journey, drifting through the subtle currents of galactic space, powered by their enduring radioisotope thermoelectric generators. Their departure from the heliosphere was not a dramatic burst, but a gradual, subtle shift in the readings of their onboard instruments, a quiet confirmation of their passage into a new, unexplored cosmic realm. The Voyager probes stand as a testament to the enduring human spirit of exploration, patiently pushing the boundaries of our knowledge and gently extending our presence into the boundless, tranquil depths of the cosmos, carrying a quiet message of humanity's curiosity to the stars. Despite its profound influence as the origin of long-period comets, the Oort cloud remains a realm of inference rather than direct observation. The Oort cloud is too distant to be directly observed, but its existence is inferred from comet observations. Its immense distance from the Sun means that any objects within it are incredibly faint, reflecting only the most minuscule amount of sunlight, making them virtually invisible to even our most powerful telescopes. The individual icy bodies are also incredibly sparse, spread out over such a vast volume that detecting them directly is an almost insurmountable challenge. Instead, scientists patiently piece together evidence of its existence by meticulously studying the behavior and characteristics of the long-period comets that occasionally visit the inner solar system. The highly eccentric, long-period orbits of these comets, which often approach the Sun from widely varying directions and from extreme distances, strongly suggest a common, distant origin point, a vast spherical reservoir of icy material far beyond the planets. This indirect yet compelling evidence allows astronomers to construct a quiet, theoretical model of the Oort cloud, painting a picture of this unseen realm. It is a testament to the subtle art of cosmic deduction, where patient observation of visible phenomena allows us to infer the existence of hidden structures, revealing the profound yet elusive architecture of our solar system's farthest reaches. A silent, enduring mystery that continues to inspire careful scientific inquiry. From the inferred, distant expanses of the Oort cloud, our attention now gently shifts to the more ephemeral, yet equally captivating, minor bodies that gracefully traverse our solar system: comets, meteors, and cosmic dust. These celestial wanderers, though often small, play significant roles in the cosmic tapestry. Comets are icy bodies that release gas and dust as they approach the sun, forming a glowing coma and a tail. Imagine a pristine, frozen nucleus, perhaps only a few kilometers across, patiently journeying through the profound cold of the outer solar system for millennia. As this icy traveler gradually nears the sun's gentle warmth, the frozen gases within its core begin to subtly sublimate, transforming directly from solid ice into gas without passing through a liquid phase. This escaping gas, carrying with it tiny particles of dust, forms a diffuse, luminous cloud around the nucleus, known as the coma, which can stretch for hundreds of thousands of kilometers. The gentle pressure of the solar wind and the sun's radiation then push this liberated gas and dust away from the sun, creating the comet's iconic, ethereal tail, often stretching for millions of kilometers across the silent vacuum of space. This luminous display, a transient yet majestic spectacle, is a beautiful testament to the subtle power of solar energy, transforming a cold, dark chunk of ice into a radiant, celestial beacon. Each comet, in its unhurried approach and departure, offers a fleeting, quiet moment of cosmic beauty, a silent, enduring dance of ice and light that captivates observers on Earth, revealing the delicate, yet profound, transformation that solar warmth can bring to these ancient, icy visitors. These luminous cosmic visitors leave behind a subtle, yet profound legacy that Earth occasionally encounters. Meteor showers occur when Earth passes through trails of dust and debris left behind by comets. As a comet gracefully orbits the sun, it continuously sheds tiny particles of dust and rocky fragments, gently dispersing them along its orbital path. These trails of cosmic debris, like invisible ribbons stretching across space, patiently remain in place long after the comet has moved on. When Earth, in its own unhurried journey around the sun, intersects one of these ancient dust trails, the countless small particles enter our atmosphere. Each tiny fragment, encountering the friction of Earth's upper atmosphere, gently heats up and vaporizes, creating a brief, luminous streak of light across the night sky. These fleeting celestial streaks, often referred to as shooting stars, appear in great numbers, creating a mesmerizing display of cosmic fireworks. The predictable timing of these meteor showers allows astronomers to patiently anticipate their arrival, offering a quiet, recurring spectacle that links our planet directly to the distant, ethereal journeys of comets. It is a testament to the enduring presence of cosmic dust and the gentle, unhurried intersection of celestial paths, a beautiful, silent reminder of the constant, subtle exchange of matter within our solar system. Each luminous streak is a quiet whisper from a distant comet, a fleeting moment of cosmic connection. To understand these luminous streaks fully, it's helpful to clarify the subtle distinctions in terminology. A meteoroid is a small piece of rock or metal in space, while a meteor is the streak of light it makes as it burns up in Earth's atmosphere. Imagine a tiny, unassuming fragment, perhaps no larger than a grain of sand or a small pebble, quietly drifting through the vast emptiness of interstellar space. This is a meteoroid, a silent wanderer, a remnant of a comet or asteroid, patiently following its cosmic trajectory. When this small piece of cosmic debris gently encounters Earth's atmosphere, the intense friction causes it to heat rapidly, glowing brightly as it vaporizes. This luminous phenomenon, the fleeting flash of light that graces our night sky, is what we call a meteor. The meteoroid itself is often completely consumed by this gentle atmospheric friction, leaving no trace behind. This distinction emphasizes the different stages of a celestial object's journey: its silent existence in space, its fiery yet brief passage through our atmospheric veil, and its potential, though rare, arrival on our planet's surface. It is a subtle, yet precise way of describing the celestial dance that unfolds above us. a quiet recognition of the transformation from a dark, unseen particle to a momentary, luminous spectacle, a testament to the gentle yet effective protection offered by our planet's atmospheric shield. And for those rare instances when these cosmic travelers endure their fiery descent. A meteorite is a meteoroid that survives its passage through the atmosphere and lands on Earth's surface. While most meteoroids are small and completely vaporized by the friction of Earth's atmosphere, larger or more robust pieces can withstand the intense heat and pressure of entry. These resilient fragments, having endured a gentle yet profound transformation during their journey, slowly decelerate as they fall through the lower atmosphere, eventually settling softly upon the Earth's surface. Once they come to rest, they are no longer called meteoroids or meteors, but meteorites, tangible pieces of extraterrestrial material that offer us a direct, quiet connection to the wider solar system. These precious cosmic samples, often dark and irregularly shaped, carry within them invaluable scientific information about the composition of asteroids, comets. Each meteorite is a silent messenger, a patiently delivered piece of cosmic history, offering scientists a unique opportunity to study primordial matter without the need for expensive space missions. Their quiet arrival on Earth's surface is a testament to their enduring journey through space and atmosphere, a gentle gift from the cosmos, patiently awaiting discovery and study, providing a tangible link to the vast, serene universe beyond our world. Adding to the constant cosmic influx, our planet is perpetually bathed in a subtle, almost imperceptible rain of extraterrestrial material. Cosmic dust, microscopic particles from asteroids and comets, constantly rains down on Earth. Imagine countless tiny motes, each no larger than a grain of pollen or a microscopic speck, gently drifting through space, remnants of ancient asteroids and the ethereal tails of passing comets. These minute fragments, shed from larger celestial bodies over billions of years, are pervasive throughout our solar system. As Earth patiently orbits the Sun, it continuously sweeps up vast quantities of this cosmic dust. Each tiny particle, encountering our planet's atmosphere, gently floats downward, eventually settling onto surfaces across the globe. While individually imperceptible, the cumulative amount of cosmic dust reaching Earth each year is substantial, estimated to be many tons. This constant, unhurried shower of extraterrestrial material is a silent, enduring connection between our planet and the wider cosmos, a gentle reminder that Earth is an integral part of a larger, dynamic system. This quiet, ceaseless influx of dust contributes subtly to our planet's geology and atmosphere, a testament to the ongoing, gentle exchange of matter within our solar system, a pervasive, yet tranquil, cosmic precipitation that has been unfolding for eons. Beyond their physical composition, some of these cosmic visitors carry a profound chemical significance. Some meteorites contain organic molecules, offering clues about the building blocks of life. When certain types of meteorites, particularly carbonaceous chondrites, are carefully analyzed by scientists, they reveal the presence of complex organic compounds, including amino acids, which are the fundamental components of proteins. These molecules are not evidence of life itself originating in space, but rather suggest that the raw chemical ingredients necessary for life's emergence were readily available and widely distributed throughout the early solar system. It is believed that these organic molecules formed patiently in the cold, dark reaches of space, perhaps within the primordial solar nebula or on the surfaces of asteroids, slowly synthesizing over vast stretches of cosmic time. Their quiet delivery to early Earth via meteorite impacts could have provided a crucial supply of these vital building blocks, gently seeding our planet with the raw materials needed for life to begin its intricate journey. This profound discovery links the gentle arrival of meteorites to the very origins of life on Earth, suggesting a deep interconnectedness between cosmic chemistry and terrestrial biology. Each meteorite, a silent, unassuming rock, holds within it a quiet, enduring whisper of life's potential, a testament to the pervasive presence of organic chemistry in the serene expanse of the universe. Finally, we return to the majestic comets themselves to appreciate the delicate balance of their structure and the immense scale of their luminous displays. The nucleus of a comet is typically only a few kilometers across, but its tail can stretch for millions of kilometers. Imagine a small, dark, icy nucleus, perhaps the size of a mountain or a small city, quietly drifting through space. This relatively modest core, a frozen reservoir of primordial material, holds the potential for truly spectacular cosmic artistry. As the comet gently approaches the Sun, the nucleus awakens, releasing gas and dust that form its brilliant coma, and, most strikingly, its expansive tail. This ethereal tail, a luminous streamer of gas and dust, can extend for an astonishing distance, often spanning tens of millions of kilometers, sometimes even reaching the distance from Earth to the Sun. This immense, graceful appendage is a testament to the subtle yet powerful forces of the solar wind and radiation pressure, which gently sweep the liberated material away from the comet's nucleus, creating a visually breathtaking, yet incredibly diffuse, structure. The immense scale of the tail, compared to the tiny nucleus, highlights the profound transformation that occurs as a comet responds to the Sun's distant warmth. It is a quiet, majestic display of cosmic interaction, a silent, luminous brushstroke across the canvas of space, revealing the delicate yet far-reaching beauty of these icy wanderers, a constant source of quiet wonder in our tranquil solar system. As we gently conclude our observations of the solar system's minor bodies, our journey now takes us back in time to the very genesis of our cosmic home, exploring the profound processes of solar system formation and its early history. Our solar system formed approximately 4.57 billion years ago from a giant rotating cloud of gas and dust known as the solar nebula. Imagine an immense, swirling expanse of cosmic material, a vast ethereal cloud of hydrogen, helium, and tiny particles of dust, patiently drifting through the interstellar medium. This primordial nebula, cold and diffuse, began its slow, unhurried transformation under the subtle influence of gravity. Perhaps a distant supernova, a gentle burst of radiance from a dying star, sent a subtle shockwave through space, causing a portion of this nebula to gently compress. As it slowly collapsed inward, the cloud began to rotate, gradually flattening into a vast, spinning disk, much like a cosmic pancake. This majestic, unhurried process, unfolding over millions of years, laid the fundamental groundwork for everything we observe in our solar system today. The solar nebula was a serene, fertile cradle, patiently nurturing the birth of our Sun and its accompanying planetary family. This ancient formative period is a testament to the elegant, self-organizing power of gravity and the abundance of cosmic raw materials, a quiet, profound beginning to our planetary story, a gentle unfolding of matter and energy that would eventually lead to the vibrant, complex system we call home. The subtle, pervasive forces within this initial cloud were the sculptors of our cosmic destiny, patiently shaping the fundamental architecture of our stellar neighborhood. Within this slowly rotating solar nebula, a crucial boundary emerged, subtly dictating the very nature of the worlds that would form. The frost line, or snow line, in the early solar nebula dictated where rocky planets, forming closer to the Sun, and gas or ice giants, forming in the colder, outer regions, would take shape. Imagine a specific distance from the nascent Sun within this swirling disk, a gentle demarcation where temperatures dropped sufficiently for volatile compounds like water, methane, and ammonia to condense into solid ice grains. Inside this frost line, where temperatures remained higher, these icy materials would have been vaporized, leaving only heavier, rocky, and metallic elements to coalesce. This subtle thermal gradient, a quiet dividing line, led to the formation of the dense, terrestrial planets, Mercury, Venus, Earth, and Mars, composed predominantly of rock and metal. Beyond the frost line, however, the abundance of solid ice grains provided much more material for accretion. Here, the nascent cores of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune, could rapidly grow to immense sizes, drawing in vast envelopes of hydrogen and helium gas. This elegant, natural separation, a testament to the subtle interplay of temperature and chemistry, profoundly shaped the fundamental composition and character of the planets, creating the distinct inner rocky worlds and outer gaseous and icy giants we observe today. It was a gentle, yet absolute, cosmic zoning, patiently guiding the evolution of our planetary family. The early solar system, while slowly coalescing, was a remarkably dynamic environment. The early solar system was a turbulent place, with frequent collisions among planetesimals, the building blocks of planets. Imagine countless small, rocky and icy bodies, ranging from meters to hundreds of kilometers in size, patiently orbiting the nascent sun. These planetesimals, the direct descendants of the dust and grit within the solar nebula, were engaged in a continuous, unhurried dance of gravitational attraction and occasional, gentle impacts. While some collisions were destructive, breaking apart smaller bodies, many were constructive, leading to the gradual accumulation of mass. Over millions of years, these repeated, subtle encounters allowed planetesimals to gently accrete or stick together, slowly growing larger and larger. This process, known as accretion, was the primary mechanism by which the planets themselves were slowly assembled, piece by piece, from this primordial debris. The turbulence was not chaotic in a violent sense, but a persistent, gentle interaction that gradually sorted and combined the raw materials of our solar system. This era of frequent, yet formative, collisions was a critical stage in planetary formation, a testament to the slow, patient processes by which vast celestial bodies are meticulously built from countless smaller fragments, a quiet, intricate construction project unfolding across the immense canvas of space. Each gentle impact contributed to the majestic growth of the planets, shaping their very foundations. At the very heart of this nascent system, the Sun itself was undergoing its own profound transformation. The Sun's formation began when the densest part of the solar nebula collapsed under its own gravity, heating up and igniting fusion. Within the swirling disk of the solar nebula, gravitational forces gradually pulled the vast majority of the gas and dust towards the center. As this central region slowly accumulated more and more mass, its gravitational pull intensified, causing it to contract further. This gentle inward collapse generated immense pressure and friction, which in turn caused the temperature at the core of this growing protostar to steadily rise. For millions of years, this central mass continued to grow hotter and denser, until the conditions within its core reached the critical threshold of 15 million degrees Celsius. At this precise moment, under unimaginable pressure, nuclear fusion gently ignited, transforming hydrogen into helium and releasing a prodigious amount of energy. This serene, yet monumental event marked the birth of our star, a quiet awakening that brought light and warmth to the nascent solar system. The ignition of fusion transformed the protostar into a true star, a stable and luminous source of energy that would sustain its planetary family for billions of years. It was a gentle, yet powerful birth, a silent promise of enduring radiance that profoundly shaped the destiny of our entire cosmic neighborhood, patiently illuminating its vast expanse. Following the Sun's gentle ignition, the remaining scattered fragments in the solar nebula continued their patient assembly. Planetesimals gradually accreted or stuck together to form larger protoplanets. Imagine the countless planetesimals, those small, rocky and icy building blocks, gently orbiting the newly formed Sun. Through a combination of gravitational attraction and subtle, slow-motion collisions, these smaller bodies began to stick together. This process, often described as a cosmic snowball effect, was not instantaneous or dramatic, but a gradual, unhurried accumulation of material. As planetesimals gently bumped into each other, they would often merge, slowly increasing their mass and thus their gravitational pull. This enhanced gravity then allowed them to attract even more surrounding material, growing larger and larger over millions of years. These growing bodies, now substantial enough to exert significant gravitational influence, became known as protoplanets, the embryonic forms of the planets we know today. This slow, patient process of accretion, driven by the fundamental force of gravity, was the primary mechanism by which the diverse worlds of our solar system were meticulously constructed from the primordial debris. It was a gentle, yet persistent, act of cosmic construction, where countless small pieces patiently combined to form the majestic, rounded forms of the planets, a silent testament to the enduring power of growth and coalescence in the early solar system. However, the early solar system was not always a picture of calm, continuous growth. It also experienced periods of more intense, though still unhurried activity. The late heavy bombardment was a period about 3.8 billion years ago, when the inner solar system experienced an unusually high number of asteroid and comet impacts. Imagine a time after the initial planet formation, when the inner planets had largely settled into their orbits, but residual populations of asteroids and comets, subtly perturbed by the gravitational migration of the giant planets, were gently scattered inward. This increased influx of smaller bodies led to a prolonged era of heightened impacts, though still spread across millions of years, leaving countless craters on the surfaces of the Moon, Mercury, and Mars. Earth, too, would have experienced this bombardment, though geological activity and erosion have long since erased most of the evidence. This period, while marked by a greater frequency of impacts, was still a gradual, unhurried process on cosmic timescales, a gentle redistribution of leftover material rather than a sudden, catastrophic event. The late heavy bombardment is a testament to the dynamic, evolving nature of the early solar system, a period where the orbits of countless small bodies were gently reshaped, leading to a profound, yet patient, sculpting of the inner planet's surfaces. It serves as a quiet reminder of the ongoing interactions that shape and refine planetary environments, a subtle, ancient echo of cosmic restlessness. Finally, the fundamental building blocks of our solar system reflect its ancient origins. The chemical composition of the solar system is primarily hydrogen and helium, inherited from the solar nebula. These two lightest elements, formed in the earliest moments of the universe during the Big Bang, constituted the vast majority of the primordial gas and dust cloud from which our sun and planets were born. Hydrogen, the most abundant element, fuels the sun's nuclear fusion, while helium is its primary product. Even though the terrestrial planets are rich in heavier elements like iron, silicon, and oxygen, and the gas giants contain other ices, the overwhelming bulk of the solar system's total mass, dominated by the sun, is still composed of these two fundamental elements. This pervasive presence of hydrogen and helium is a direct, quiet link to the universe's earliest moments, a testament to the primordial soup from which all celestial bodies eventually coalesced. It is a serene reminder that our solar system, with all its intricate complexity and diversity, is ultimately built from the simplest and most abundant ingredients in the cosmos. This fundamental chemical signature, patiently preserved throughout our system, underscores the deep, enduring connection between our local cosmic neighborhood and the grand, universal tapestry of matter and energy. From the primordial chemical signatures that define our solar system's origins, we now turn our attention to some of the unique phenomena and precise measurements that reveal the intricate workings of our cosmic neighborhood. One such elegant interaction is observed in the gravitational ballet of celestial bodies. Orbital resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other, like some of Jupiter's moons. Imagine a delicate, rhythmic dance performed by celestial partners, where their orbital periods are in a simple, harmonious ratio. For instance, Among Jupiter's Galilean moons, Io, Europa, and Ganymede are locked in a beautiful 1 to 2 to 4 orbital resonance. This means that for every one orbit of Ganymede, Europa completes exactly 2 orbits, and Io completes precisely 4. This consistent, periodic gravitational tug prevents the moons from settling into perfectly circular paths, subtly stretching and squeezing their interiors. This gentle, yet persistent, tidal stress generates internal heat, which is responsible for the intense volcanism on Io and the subsurface liquid ocean on Europa. Orbital resonance is a testament to the long-term gravitational interactions that shape planetary systems, a quiet, enduring rhythm that governs the movements and even the internal geology of celestial bodies. It is a subtle, yet powerful manifestation of cosmic harmony, revealing how the patient, unhurried dance of gravity can create profound and lasting effects throughout our solar system. This elegant interplay of forces illustrates the deep, interconnected nature of celestial mechanics, a serene and continuous ballet that defines these distant worlds. At the very foundation of how we perceive and measure these cosmic phenomena lies a fundamental constant of the universe. The speed of light is the fastest known speed in the universe. This incredible velocity, an ultimate cosmic speed limit, is not merely a rapid movement, but a fundamental property of the fabric of space-time itself. Nothing with mass can ever reach or exceed this speed, making light the fastest messenger across the vast, silent expanses of the cosmos. This constant, unwavering speed allows light to traverse immense distances, carrying information from distant stars and galaxies to our telescopes and indeed to our very eyes. It is a quiet, profound truth that shapes our understanding of cosmic distances and the nature of time in the universe. The serene, unhindered journey of light, always at this ultimate speed, ensures that every observation we make of a celestial object is a glimpse into its past. This universal speed limit is a testament to the elegant, unchanging laws that govern our universe, a silent, enduring constant in the ever-unfolding cosmic drama, a fundamental principle that underpins all our attempts to measure and comprehend the vastness around us. This inherent delay in light's journey has a fascinating consequence for our cosmic observations. Observing distant objects in the solar system allows us to look back in time, as their light takes time to reach us. When we gaze upon the majestic rings of Saturn, or the cloud-banded face of Jupiter, or even the subtle reddish hue of Mars, we are not seeing them exactly as they are at this very instant. Instead, we are witnessing them as they appeared minutes or even hours ago. For instance, light from Jupiter takes about 33 to 53 minutes to reach Earth, depending on our planet's positions. Light from Saturn takes over an hour. This cosmic time delay is a gentle reminder of the vast distances involved, turning our telescopes into quiet, patient time machines. Each photon that enters our eye or our instrument carries with it a snapshot of the past, allowing astronomers to study the evolution of planetary features, track the movements of moons, and monitor the subtle changes in distant atmospheres. It is a profound yet serene aspect of cosmic observation, where the very act of looking outward is also a journey backward through time, revealing the ongoing story of our solar system's gentle, unhurried evolution. This quiet, temporal dimension adds a layer of depth to every celestial view, offering a unique perspective on the dynamic history of our cosmic neighborhood. Furthermore, our entire solar system is not a fixed, static entity, but a dynamic traveler within a much grander structure. The solar system is not static, but is constantly moving through the Milky Way galaxy. Imagine our sun, with its retinue of planets, asteroids, and comets, patiently orbiting the galactic center, completing one full revolution roughly every 250 million years. This immense, unhurried journey carries us through the spiral arms of our home galaxy, a vast, majestic dance through a sea of billions of stars, gas, and dust. As we travel, our solar system gently bobs up and down and oscillates inward and outward relative to the galactic plane, a subtle, rhythmic motion within the galaxy's gravitational embrace. This continuous silent movement means that our cosmic neighborhood is constantly encountering new regions of interstellar space, subtly influencing the environment around us. It is a profound yet serene realization that our entire planetary home is a single, cohesive unit, gracefully navigating the immense, complex architecture of the Milky Way. This constant, unhurried galactic voyage underscores the dynamic nature of the cosmos, a testament to the grand, pervasive gravitational forces that orchestrate the movements of stars and planetary systems on truly monumental scales. As we ponder the potential for life beyond Earth, a vital concept guides our search. The concept of a habitable zone defines the region around a star where conditions might allow for liquid water on a planet's surface. Imagine a gentle, orbital sweet spot around any given star, a specific range of distances where a planet could maintain temperatures suitable for water to exist in its liquid state. This Goldilocks zone is neither too close to the star, where water would quickly boil away, nor too far, where it would perpetually freeze solid. The presence of liquid water is considered a fundamental requirement for life as we understand it, making this zone a crucial focus for astrobiologists. The size and location of a star's habitable zone depend on its size and luminosity. Hotter, more luminous stars have wider, more distant habitable zones, while cooler, dimmer stars have narrower, closer zones. Earth, orbiting within our Sun's habitable zone, is a prime example of a world where conditions have allowed liquid water, and thus life, to flourish for billions of years. This quiet, theoretical boundary provides a serene framework for our search for exoplanets that might harbor life, a gentle guide in the vast cosmic quest for other habitable worlds, patiently reminding us of the delicate balance required for life's emergence. Yet, even our life-giving Sun, in its serene constancy, exhibits dynamic behaviors that can subtly influence our planetary home. The Sun's activity, like solar flares and coronal mass ejections, can impact Earth's technology and auroras. Imagine sudden, gentle bursts of intense radiation or vast, slow clouds of magnetized plasma gently erupting from the Sun's surface, slowly propagating through space. These solar phenomena, while a natural part of our star's 11-year activity cycle, can interact with Earth's magnetic field and atmosphere. Solar flares release powerful bursts of X-rays and ultraviolet radiation that can subtly disrupt radio communications and satellite signals. Coronal mass ejections, or CMEs, release colossal bubbles of charged particles that, upon reaching Earth, can induce geomagnetic storms. These storms, while not physically harmful on the surface, can cause gentle fluctuations in power grids and subtly interfere with satellite operations. However, a more beautiful consequence of these solar events is the creation of the auroras, the mesmerizing northern and southern lights, as charged particles gently interact with Earth's atmospheric gases near the poles. This delicate interplay between the Sun's dynamic processes and Earth's protective magnetic field is a testament to the profound interconnectedness of our solar system. A quiet reminder that even our distant star actively, yet gently, shapes the environment of our home planet, creating both subtle challenges and breathtaking celestial displays. Finally, a familiar and fundamental characteristic of our own planet dictates the very rhythm of our lives. The tilt of Earth's axis is responsible for our seasons, as different parts of the planet receive more direct sunlight throughout the year. Imagine Earth gracefully orbiting the Sun, not perfectly upright, but with its rotational axis gently tilted at an angle of approximately 23.5 degrees relative to its orbital plane. This constant, unwavering tilt means that as Earth makes its unhurried journey around the Sun, different hemispheres are alternately angled towards or away from our star. When the northern hemisphere is tilted towards the Sun, it receives more direct and concentrated sunlight, leading to warmer temperatures and longer days, our summer. 6 months later, as Earth continues its patient orbit, the northern hemisphere is tilted away from the sun, receiving less direct sunlight, resulting in cooler temperatures and shorter days, our winter. The southern hemisphere experiences the opposite seasons at these times. This elegant, predictable axial tilt is the primary driver of our planet's seasonal cycle, a gentle, rhythmic variation that profoundly influences climate, ecosystems, and human activity. It is a testament to the enduring stability of Earth's orientation in space, a quiet, celestial mechanism that ensures the regular, unhurried progression of our seasons, painting our world in a continuous, beautiful cycle of change and renewal, a fundamental aspect of Earth's serene, life-sustaining environment. From the gentle, rhythmic progression of Earth's seasons, our thoughts now turn to humanity's profound quest for understanding life beyond our home world, and to the deep future that patiently awaits our solar system. In this serene exploration, some celestial bodies stand out with particular promise. Beyond Earth, moons like Europa and Enceladus are considered the most promising places in our solar system to find extraterrestrial life due to their subsurface oceans. These two icy satellites, Europa orbiting the colossal Jupiter and Enceladus circling the ringed Saturn, are both cloaked in thick, brilliant shells of water ice. Yet, beneath these frozen exteriors, scientists believe vast, tranquil oceans of liquid water lie hidden, shielded from the harsh radiation of space. On Europa, observations of its fractured surface, which shows signs of subtle geological activity and dynamic ice tectonics, along with magnetic field measurements, strongly suggest the presence of this deep, liquid realm. Similarly, Enceladus actively vents plumes of quiet geysers that serve as direct evidence of a subsurface reservoir, gently exhaling its secrets into the vacuum. The presence of liquid water, a fundamental requirement for life as we know it, makes these moons incredibly compelling candidates in the patient search for microbial life beyond Earth. They float serenely in the outer solar system, two distant icy worlds holding the profound quiet promise of alien oceans and the potential for life to have found a way to flourish in the profound depths. Far from the direct warmth of the sun, their existence expands our understanding of where life might emerge, pushing the boundaries of the habitable zone to include worlds warmed not by direct starlight, but by internal subtle forces. This quiet potential illuminates these moons as beacons of hope in the grand cosmic quest, inviting future, gentle explorations to uncover their hidden aquatic wonders. The secret to these hidden liquid worlds lies in a subtle yet powerful cosmic mechanism. Tidal heating, caused by gravitational interactions with larger planets, keeps the subsurface oceans of some moons liquid. Imagine a delicate, continuous tug-of-war unfolding between a moon and its massive parent planet. As Europa and Enceladus orbit their respective gas giants, Jupiter and Saturn, they are subjected to immense, varying gravitational forces. These forces gently stretch and compress the moon's interiors, subtly deforming their rocky cores and icy mantles. This constant, gentle squeezing and releasing generates internal friction, which in turn produces a steady, persistent warmth deep within their structures. This internally generated heat, much like the gentle flexing of a material, is sufficient to melt vast quantities of ice, creating and sustaining the subsurface liquid oceans, even in the frigid environment of the outer solar system. The closer a moon orbits its giant planet, and the more elliptical its orbit, the stronger these tidal forces become, leading to more intense internal heating. This elegant process of gravitational energy conversion ensures that these distant oceans remain in a liquid state, providing a stable environment where complex chemistry and potentially life could patiently develop over billions of years. It is a testament to the pervasive, subtle power of gravity, not just as a force that shapes orbits, but also as a quiet, internal furnace that nurtures the possibility of life in unexpected corners of our cosmic neighborhood. A gentle, enduring warmth, sustaining liquid realms in the profound cold. As we peer into the distant future, The ultimate fate of our Sun, and by extension, our solar system, unfolds in a series of grand, unhurried stellar transformations. In about 5 billion years, the Sun will expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth. This profound change is a natural and inevitable stage in the life cycle of a star like our Sun. As its core gradually depletes its hydrogen fuel, it will begin to fuse helium, causing its outer layers to gently swell outward, cooling as they expand. This slow, majestic expansion will transform our familiar yellow dwarf into a colossal red giant, its luminous surface growing to an immense size. Mercury and Venus, being the innermost planets, will undoubtedly be absorbed into the Sun's vast, expanding envelope, gently melting away into its fiery embrace. For Earth, the fate is less certain, but still profoundly significant. While some models suggest Earth might just escape outright engulfment, its oceans will boil away, and its surface will become irrevocably scorched by the Sun's immense heat and proximity. This unhurried, gentle swelling of our star marks the end of its main sequence stability, transforming our once habitable zone into a searing inferno. It is a testament to the patient, predictable evolution of stars, a quiet, inevitable cosmic destiny that will slowly, elegantly reshape the inner architecture of our solar system, a profound yet serene transition from a life-giving star to a sprawling, cooler giant. Following this immense expansion, our Sun will undergo another serene yet dramatic transformation. After its red giant phase, the Sun will shed its outer layers, forming a planetary nebula, and its core will become a white dwarf star. Imagine the Sun's vast, expanded outer atmosphere gently detaching and drifting away into space, creating an ethereal, luminous shell of gas and dust. This beautiful iridescent cloud, known as a planetary nebula, will slowly expand and dissipate over tens of thousands of years, painting the cosmos with its vibrant, transient beauty. This gentle exhalation of material will leave behind the Sun's dense, compact core, a quiet remnant known as a white dwarf. This white dwarf will be roughly the size of Earth, but with a mass comparable to the original Sun, making it incredibly dense. It will be a slowly cooling cosmic ember, radiating its remaining stored heat into space for trillions of years, a patient, enduring testament to the star it once was. This final graceful act of stellar evolution marks the Sun's transformation from a luminous giant into a silent, compact, stellar corpse. It is a profound, yet serene, celestial farewell, a quiet return of its constituent elements to the cosmos, gently enriching the interstellar medium for future generations of stars and planets, a patient, unhurried conclusion to its active stellar life. Our current location within the vast expanse of the Milky Way galaxy offers a subtle advantage for the long-term stability of life. The solar system is located far from the galactic center in a quieter region of the Milky Way, which may be beneficial for life. Imagine our galaxy as a colossal, swirling city of stars, with a bustling, densely packed downtown at its core. The galactic center is a region of intense activity, filled with supermassive black holes, frequent supernovae, and dense clusters of stars, all contributing to a more turbulent and energetic environment. Our solar system, however, resides in one of the Milky Way's quieter spiral arms, approximately 27,000 light-years from the bustling galactic core. This more serene location offers a protective distance from the potentially disruptive forces and high-energy radiation that are more prevalent in the central regions. The calmer environment allows for a more stable and prolonged period of planetary evolution and the gentle emergence of complex life, free from frequent catastrophic cosmic events. It is a testament to the fortunate positioning of our cosmic home, a quiet, enduring haven in the vast, dynamic tapestry of our galaxy. This tranquil placement ensures a long, unhurried period of cosmic calm, fostering the conditions necessary for life to patiently thrive, a subtle yet profound benefit for our habitable world. In our ongoing quest to understand life's presence in the universe, scientists are diligently and patiently searching for subtle clues. Scientists are actively searching for biosignatures, indicators of past or present life, on other solar system bodies. This meticulous search involves deploying sophisticated spacecraft and instruments to analyze the atmospheres, surfaces, and subsurface environments of promising worlds such as Mars, Europa, and Enceladus. Biosignatures can take many forms: specific chemical compounds or combinations of molecules that are typically produced by biological processes, unusual isotopic ratios that suggest biological activity, or even complex organic molecules that are the building blocks of life. For instance, the detection of methane in Mars' atmosphere, while not conclusive, is a subtle hint that warrants further investigation. The careful analysis of samples returned from other bodies or in situ measurements by robotic landers offers the best chance to identify these elusive indicators. This patient, unhurried scientific endeavor is driven by a deep curiosity about our place in the cosmos, a gentle yet persistent effort to uncover whether life has emerged elsewhere in our immediate cosmic neighborhood. It is a testament to humanity's enduring spirit of inquiry, a quiet, systematic search for the subtle whispers of life beyond Earth, patiently expanding our understanding of biology's reach. Ultimately, as cosmic time continues its unhurried flow, the grand narrative of our solar system will reach its final, serene chapter. The ultimate fate of the solar system is to slowly disperse as the sun becomes a white dwarf and planets eventually drift away or are ejected. After our sun completes its luminous life cycle and transforms into a cooling white dwarf, its gravitational influence on the remaining planets will subtly diminish as it loses a significant portion of its mass during the planetary nebula phase. This gentle weakening of its gravitational tether will cause the remaining outer planets, now orbiting a much smaller, denser star, to gradually drift into wider and wider orbits. Over truly immense timescales, spanning trillions of years, the gravitational perturbations from passing stars in the galaxy, though rare, will become increasingly effective at subtly nudging these planets. These gentle gravitational interactions could eventually cause some planets to be slowly ejected from the solar system entirely, sending them on solitary journeys through interstellar space. Others might remain bound to the white dwarf, but in profoundly altered, distant orbits. This final, unhurried dispersal is not a violent end, but a slow, elegant unbinding, a gradual fading of our planetary family into the vastness of the cosmos. It is a serene, patient conclusion to a billions of years-long story, a testament to the enduring, subtle forces of gravity and the pervasive, unhurried rhythm of cosmic change, as our solar system gently dissolves back into the grand tapestry of the universe. From the which, we now lift our gaze to see where our entire solar system resides within that magnificent, sprawling design. Our solar system is part of the Orion arm of the Milky Way galaxy, one of its spiral arms. Imagine, if you will, our home galaxy, the Milky Way, as a colossal flat disk of billions upon billions of stars, vast clouds of gas, and delicate cosmic dust, all slowly turning with an immense, unhurried grace in the profound silence of space. From a distant vantage point, it would unfurl before our eyes as a luminous, majestic pinwheel with elegant, curving spiral arms extending outward from a brilliant, densely packed central bulge. Our own sun, with its accompanying retinue of planets, dwarf planets, asteroids, and comets, resides nestled gently within one of these ethereal, luminous arms. Specifically, we are located in what astronomers refer to as the Orion Arm, which is sometimes also known as the local arm due to our presence within it. This particular spiral arm is not one of the Milky Way's largest or most dramatically prominent, but rather a more subtle, meandering offshoot, a quiet, flowing current of stars and nebulae situated patiently between two of the galaxy's more substantial and visually striking arms, the Perseus arm and the Sagittarius arm. This tranquil, somewhat secluded placement bestows upon our solar system a truly serene existence. We are situated far from the bustling, more turbulent and potentially chaotic activity that often characterizes the denser, more energetic regions closer to the galactic core, where gravitational interactions are more frequent and intense, and where stellar explosions might occur with greater regularity. Within the gentle confines of the Orion Arm, the vast populations of stars, the expansive clouds of interstellar gas, and the delicate lanes of cosmic dust are distributed in a remarkable, quiet balance, allowing for long, uninterrupted periods of stability. These conditions are profoundly conducive to the patient development and sustained evolution of complex life, providing a haven of cosmic calm for billions of years. We are positioned approximately 2/3 of the way out from the galactic center, a distance that offers a clear, relatively unobstructed view of both the inner and outer regions of the Milky Way from Earth's serene perspective. The Orion Arm itself is an immense, elongated structure, a flowing river of stars and nebulae patiently tracing its path as the entire galaxy slowly, majestically rotates. It is a quiet, enduring journey through the galactic landscape, a testament to the grand, unhurried movements that govern the larger, more intricate structures of the cosmos. Our presence within this specific arm ensures a gentle, stable environment, a calm harbor within the immense swirling currents of our home galaxy, allowing for billions of years of peaceful cosmic evolution. The subtle, pervasive gravitational forces of the galactic disk gently guide our solar system on its long, patient orbit, a silent, majestic dance within the grand celestial ballet of the Milky Way. This sense of belonging to a larger, yet equally serene structure underscores the deep interconnectedness of all cosmic entities, from the smallest asteroid to the largest galaxy, each playing its unique part in the vast, elegant, and unhurried unfolding of the universe. Despite this intricate and serene placement within the galaxy, the sheer scale of our local cosmic neighborhood can be profoundly humbling when compared to the galactic whole. The solar system is vast, spanning over 100,000 astronomical units, yet it is a tiny speck within the Milky Way. To truly appreciate this immense contrast, let us gently recall the measure of an astronomical unit, or AU, which serves as a fundamental cosmic yardstick. One our sun, a distance of c, imagine a vast ethereal sphere of influence, a silent, pervasive dominion extending outward from our sun for a staggering 100,000 of these units. This immense expanse encompasses not just the familiar orbits of all the major planets and dwarf planets, but also the distant icy realm of the Oort cloud, which we explored earlier as the source of long-period comets. This colossal sphere, representing the outermost boundaries of the Sun's primary gravitational dominion, is truly immense by any human standard of measurement. It is a vast expanse of space where our star's gentle, yet enduring, gravitational pull still holds sway over countless icy bodies, patiently guiding their millennia-long orbits. Within this immense, tranquil volume, the Sun's light becomes increasingly dim, a distant, gentle beacon against the profound darkness, a quiet, pervasive presence that slowly fades into the cosmic background. Yet, when we gently zoom out, when our perspective quietly shifts to embrace the truly colossal scale of the entire Milky Way galaxy, this immense solar system, which felt so boundless just moments ago, shrinks into an almost imperceptible point. Our home galaxy itself spans an astonishing distance of approximately 100,000 light-years in diameter. A light-year, as we know, is the distance light travels in 1 year. And it is a measure so vast that it represents roughly 9.5 trillion kilometers, or almost 6 trillion miles. To grasp the enormity of this galactic scale, consider that 1 light-year is approximately 63,241 astronomical units. Therefore, our solar system, with its 100,000 AU span, represents only a tiny fraction of a single light year, making it an infinitesimally small dot within the galaxy's grand, majestic design. Despite the incredible vastness and complexity of our local planetary system, we are but a minuscule, almost invisible component of the grand galactic tapestry. This humbling perspective encourages a deep sense of quiet wonder and reverence for the boundless scale of the cosmos, gently reminding us that even the most expansive local structures are mere whispers within the truly unimaginable dimensions of the universe. Our solar system, in its quiet, unhurried journey, is a delicate, luminous particle within the majestic, swirling ocean of the Milky Way, a testament to the elegant hierarchy of cosmic scales, where local immensity is constantly dwarfed by the ever greater expanse beyond. The gentle, silent presence of our tiny system within this galactic behemoth underscores the profound beauty and serenity of cosmic existence, a constant reminder of our small, yet cherished place in the grand scheme. Finally, as we contemplate the outermost limits of our solar system, it is important to understand that these cosmic frontiers are rarely abrupt or sharply defined lines, but rather zones of gentle transition. The boundary of the solar system is not sharply defined, but gradually fades into interstellar space through the Oort cloud. Imagine not a rigid, impermeable fence or a clear, definitive dividing wall, but rather a subtle, ethereal transition zone, an immense and diffuse region where the pervasive influence of our sun slowly, imperceptibly wanes, and the gentle, pervasive presence of the interstellar medium begins to assert itself. This gradual fading occurs primarily within the vast, spherical realm of the Oort cloud, which we previously explored as the distant, icy reservoir of long-period comets. In this outermost region, the sun's gravitational grip, while still present and strong enough to hold these icy bodies in orbit, becomes incredibly tenuous, allowing for a delicate interplay with the subtle gravitational fields of nearby stars and the pervasive magnetic currents of the wider galaxy. The icy bodies of the Oort cloud are still gravitationally bound to our sun, but their orbits are so incredibly elongated and their distances so immense that they are also subtly influenced by external galactic forces. As one travels further and further outward through this vast, tranquil expanse, the density of these solar-bound objects gradually diminishes, becoming increasingly sparse, and the characteristics of interstellar space, its diffuse gas, its microscopic dust, and its faint magnetic fields, become more and more dominant. There is no precise, universally agreed upon point where the solar system abruptly ends and interstellar space definitively begins. Instead, it is a continuous, unhurried merging, a serene blend of two distinct cosmic environments. This gentle, indistinct boundary reflects the fluid, interconnected nature of the cosmos, where influences gently overlap and diminish over vast distances, rather than terminating abruptly. Processes that shape cosmic frontiers, painting a picture of a universe where transitions are rarely stark, but rather unfold with an elegant, unhurried grace. This quiet, gradual fading into the interstellar medium reinforces the idea that our solar system is not an isolated island, but an integral, seamlessly woven thread within the larger, boundless tapestry of the galaxy, a serene, enduring testament to the interconnectedness of all cosmic realms. The absence of a sharp edge offers a sense of fluidity and endless possibility, a soft, inviting threshold into the profound unknown, beyond the familiar comforts of our home system. A gentle whisper of the cosmic ocean that lies beyond. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies, from the intricate web of dark matter to the faint whispers of cosmic background light. You have traveled through starry nurseries, soared along luminous spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. You are part of this cosmic story, not just an observer, but but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.